Welcome. Tonight, our journey takes us back. We travel to a time when the familiar outlines of our world dissolve, when the maps we know become meaningless. We are going to a time when the Atlantic Ocean did not exist, a time when the Pacific was not a separate vast blue but part of a single planet-spanning sea. We journey to the age of Pangea. Imagine for a moment standing on the coast of what is now North America, looking east. There is no ocean, there is only land. Imagine being able to walk, crossing the ancient folded roots of mountains, and finding yourself in what will one day be called Africa. Imagine walking south across vast, dry plains and arriving in the land we now know as Antarctica. This was a world without the great oceanic barriers that define our own, a world of one land and one sea. This single colossal landmass, Pangea, a name derived from ancient Greek, meaning all lands, stretched nearly from the South Pole to the North Pole. It was a continent shaped not like our familiar scattered puzzle pieces, but like a great letter C, cupping a sheltered ancient sea. Its very existence fundamentally altered the planet. It changed the flow of the oceans. It rewrote the rules of the climate, creating a world of brutal extremes. And it set the stage for an evolutionary drama unlike any other. On our voyage tonight, we will explore this lost world. We will feel the unimaginable dryness of its interior, a desert heartland thousands of kilometers from the nearest drop of ocean moisture. We will listen to the distant roar of the mega monsoons that battered its coastlines, a seasonal deluge of almost unimaginable power. We will also meet the creatures that called this world home. This was not the age of dinosaurs. This was a time before them, a time ruled by a different and perhaps stranger dynasty of life. We will encounter the vast herds of decinodonts, tusked, beaked herbivores that wandered the plains in the millions. We will walk in the shadows of the Gorgonopsians, the saber-toothed apex predators of this ancient world. Monsters that ruled the land millions of years before the first Tyrannosaurus ever walked. And finally, we will stand as silent witnesses to the end of this world. We will journey into the heart of the greatest catastrophe life has ever known, the Great Dying. A planetary cataclysm that extinguished perhaps 95% of all life in the seas and 70% of life on land. We will see how Pangaea itself, this great unified continent, may have held the seeds of its own destruction. And we will see how from the ashes of this apocalypse, a new world was born. A world that would finally set the stage for the rise of the dinosaurs. So, before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who is joining us from around the world, gathering for this journey into deep time. Now, dim the lights. Perhaps turn on a fan for that soft background hum. The sound perhaps of an ancient wind blowing across a land that no longer exists. A wind that has traveled 300 million years to reach you. And let's ease into tonight's journey together. Before we can truly understand the world of Pangea, we must first wind the clock back just a little further. We must first appreciate the world it replaced. This great supercontinent, this unified landmass, was not the planet's normal state. For hundreds of millions of years before its birth, the Earth was a world of scattered continents and wide ancient oceans. It was a fragmented planet, perhaps looking more familiar to our modern eyes, though the names and positions of the lands were entirely different. If we were to drift back in time to the period just before the Great Assembly, to the era geologists call the Devonian or the early Carboniferous, we would see a world of separate, bustling land masses. To the south, there was a truly colossal supercontinent, a giant in its own right, known as Gondwana. This was the great southern anchor of the world, a vast assembly that already contained the future cores of South America, Africa, Antarctica, Australia, and India, all locked together in a different configuration. It was a massive piece of the planetary puzzle, drifting slowly northward. To the north of it, scattered across the warmer tropical latitudes, were the northern continents. There was Laurentia, the ancient rocky heart of what would become North America. For much of this time, it lay on its side, basking in the equatorial sun. Nearby was Baltica, the future northern Europe, which had already, in a previous, smaller collision, fused with Laurentia to form a combined continent we sometimes call Euramerica. And further east lay the separate, lonely continent of Siberia. These were worlds unto themselves, and they were separated by vast, deep, and now vanished oceans. The Iapetus Ocean, an early ancestor of the Atlantic, had already closed, its sutured wound forming mountains as Laurentia and Baltica joined. But the great ocean of this age, the primary body of water separating the north from the south, was the Reich Ocean. Imagine this forgotten sea. It was wide, perhaps as wide as the Atlantic is today, teeming with a strange and wonderful explosion of life. This was the Age of Fishes. The waters of the Reich Ocean were filled with bizarre armored placoderms, like the terrifying Dunkleosteus. The first sharks were weaving through its currents, and, crucially, the first lobe-finned fish, our own distant ancestors, were using their sturdy fins to explore the shallow, muddy estuaries. On the shores of these continents, another revolution was taking place. The first true forests were taking root. Tall, tree-like ferns and primitive lycopod trees like Archaeopteris were stretching towards the sky, creating the planet's first complex, shaded ecosystems. The air was becoming richer in oxygen, and the first four-legged tetrapods, still looking much like amphibious fish, were tentatively hauling themselves onto the land. It was a world of incredible innovation. A green, blue, living planet, defined by its diversity of environments, its separate lands, and its wide oceans. Life was diversifying, specializing, and conquering new realms. But this fragmented world was living on borrowed time. Deep beneath the floor of the Reich Ocean, the tectonic plates were moving. The relentless heat of the Earth's mantle, the engine of continental drift, was pulling these scattered lands together. The great southern continent, Gondwana, continued its unstoppable, slow-motion journey northward. The northern continents of Euramerica and Siberia were drifting south. The Reich Ocean, that vast, life-filled sea, was shrinking. Year by year, millennium by millennium, its waters were vanishing, its seafloor consumed back into the Earth's mantle in a process we call subduction. The gap was closing. These separate, vibrant worlds, each with its own unique story, were being drawn into the same gravitational well, pulled toward an inevitable planetary-scale rendezvous. The stage was being set for the most dramatic geological event of the last 500 million years, the great collision that would erase this fragmented world, and from its pieces forge the single, unified supercontinent of Pangea. This was a collision that defies our human sense of time. It did not happen with the sudden violence of a car crash. It was a gradual, inexorable, and impossibly powerful event playing out over a span of 60 million years. Imagine two giants, each the size of a continent, sliding toward one another at the speed your fingernails grow. For millennia, they would seem motionless, but over the deep expanse of geological time, that slow, patient movement becomes an unstoppable force. The Reich Ocean, which had once rivaled the Atlantic in size, continued to narrow. Its ancient seafloor, heavy and cold, dove deeper and deeper into the mantle beneath the northern continents. The gap closed, and then, sometime around 350 million years ago, in the midst of the Carboniferous period, the two shorelines met. The first touch was not a gentle kiss. It was the beginning of a geological catastrophe. Try for a moment to imagine the sound of this event. It is not the sharp crack of a single earthquake, but the continuous low-frequency groan of a planet rearranging itself. It is the sound of two continental crusts, each kilometers thick, grinding against one another, buckling and shattering. It is the sound of rock under unimaginable pressure and heat, folding like fabric. It is the sound of a slow-motion tectonic scream, a single sustained tremor lasting for 60 million years. As the great southern landmass of Gondwana pushed relentlessly into the northern landmass of Euramerica, the land in between had nowhere to go. The sediments that had lined the seafloor of the Reich Ocean, the ancient coastal plains, the volcanic islands that had dotted the sea, all of it was caught in the vice. Like a colossal rug being pushed against a wall, the crust began to fold. Great masses of rock, thousands of feet thick, were thrust upwards, scraped from their foundations, and piled on top of one another. The ground shuddered, fractured, and rose. In the heart of this collision zone, the Earth's surface was lifted kilometer by kilometer towards the sky. This was the birth of a mountain range. Not just a mountain range, but perhaps the largest, longest mountain range the world had ever seen. The central Pangean mountains. Today, we know their worn-down ancient roots. The Appalachian Mountains in North America, particularly their southern and central portions, are the deep, eroded remnants of this colossal event. The mountains of Ireland and Scotland, the Variscan belt that runs through France, Germany, and Spain. These are all scars from that same, single, ancient collision. But in their time, in the late Carboniferous and early Permian, these were not the gentle, rolling hills we see today. They were young, jagged, and terrifyingly high. They were the Himalayas of their day, perhaps even grander, a wall of rock and ice splitting the new supercontinent in two, a testament to the violent power that had forged this new world. For millions of years, this process continued. The landmass of Siberia, drifting in from the east, eventually collided with the rest of the mass, adding its own mountains, the Urals, to the chain. The Reich Ocean vanished from the map forever, its waters displaced, its memory sealed in a line of crumpled rock. The fragmented world was gone. The puzzle pieces, after hundreds of millions of years apart, had finally locked together. The Earth, for the first time since the breakup of the ancient, simpler continent of Rodinia, was once again almost whole. This was the forge, and the thing that emerged from it, cooling and settling after the violence of its creation, was Pangea. And so, by about 335 million years ago, as the Carboniferous period drew to its close, the Great Collision was largely complete. The tectonic dust was settling. The immense, planet-spanning mountain range now stood as a raw, fresh scar, dividing the newly formed landmass. The old world of scattered continents and wide intervening oceans was gone. In its place stood Pangea, the name itself, coined by Alfred Wegener, the father of continental drift, comes from the ancient Greek. Pan meaning all, and Gaia meaning earth or land. All lands. And that is precisely what it was. For the first time in hundreds of millions of years, nearly all of the planet's major continental blocks were locked together into a single, cohesive, colossal whole. Let us try for a moment to visualize the map of this new world. It looks nothing like our own. The supercontinent of Pangaea was not a simple circular blob. It was an immense landmass, curved like a giant letter C, or perhaps a cosmic Pac-Man facing east. It was oriented vertically on the globe, stretching nearly from the South Pole all the way to the high northern latitudes, almost reaching the North Pole. The scale is difficult to comprehend. The southern half of this sea was the old vast continent of Gondwana. This single piece contained the future South America, Africa, Antarctica, Australia, and India, all still locked tightly together. The northern half of the sea was the newly assembled northern continent, containing the future North America, Europe, and Siberia, all now sutured to Gondwana by the fresh stitches of the central Pangean mountains. Imagine the consequences of this geography. There were no separate continents, each with its own unique evolutionary path, its own isolated fauna. It was now one contiguous land. An animal born in what would one day be Siberia could, in theory, over many generations, walk to the land that would one day be Antarctica. This unbroken expanse of land would have profound and devastating consequences for the planet's climate. And this new arrangement of land, this single supercontinent, meant there was also a new arrangement of water. The planet's oceans, which had once been a complex network of interconnected seas, the Reich, the Iapetus, and others, were now consolidated into just two main bodies of water. The first was the one that dominated the globe, surrounding Pangea on all sides, filling the rest of the planet's surface, was a single, truly global ocean. This was Panthalassa, the All-Sea. The second was the smaller, though still vast ocean that filled the great eastern-facing bay of Pangea's sea shape. This was the Paleotethys Ocean, a deep, warm, tropical sea cupped in the protective arms of the supercontinent. This was the world of the late Carboniferous and the coming Permian period, a planet redefined, one land and effectively one ocean. This new geography was a new stage, and it demanded new rules for the life that inhabited it. The old, familiar coastal environments, the shallow seas that had defined the fragmented world, were drastically reduced. In their place, a new, harsh, and utterly vast environment had been created, the continental interior. Life would now have to adapt to this strange, unified, and unforgiving world. The gentle, fragmented Earth was gone, replaced by a world of scale, a world of extremes. The age of Pangea had truly begun. With the birth of Pangea, the world's land was forged into one. But this consolidation of land created its equal and opposite, the consolidation of water. In the old fragmented world, there had been many oceans, each with its own name, its own currents, its own character. The Iapetus, the Reich. These were complex bodies of water that separated continents, creating diverse coastlines and unique marine environments. Now they were gone. In their place, there was only one. As Pangea coalesced, it was surrounded on all sides by a single, unbroken, globe-spanning body of water. Geologists call it Panthalassa, the All-Sea. Let us try for a moment to comprehend the scale of this ocean. It was not like the Atlantic or the Pacific or the Indian. It was all of them, and more. It was a single, continuous expanse of water that covered perhaps 60 to 70% of the Earth's entire surface. Imagine floating in the center of this ocean. In any direction you look, there is only water. The nearest land might be 10,000 kilometers away. There are no continents to interrupt the horizon, no land masses to break the fetch of the wind. The waves here, born in a storm thousands of kilometers away, could travel halfway around the planet before finally crashing onto the single, distant shore of Pangea. Imagine the view from the moon. One side of the planet would be the familiar brownish green and red rock of the supercontinent, the great Sea of Pangea. The other side, the other entire hemisphere, would be an endless, deep, unbroken blue. This was the ultimate ocean. Its depths were likely profound, its center a vast, watery desert, far from the nutrient-rich runoff of the land. Its currents, too, would have been different from the complex looping patterns we know today. With no continents to deflect and complicate their flow, the ocean currents of Panthalassa were likely simpler, slower, and more massive. Perhaps a single colossal gyre dominated each hemisphere, a slow, planetary-scale whirlpool that took centuries to complete a single circuit, distributing heat or cold across the globe in a simple, stable pattern. And what of the coastline? In our modern world, we have tens of thousands of kilometers of varied, complex coastlines. We have sheltered bays, inland seas, archipelagos, fjords, and deltas. Pangea had only one. A single, continuous shoreline, the longest coastline the world has ever known, wrapping around the entirety of the supercontinent. Life, which had flourished in the shallow, protected seas of the Old World, now found itself clinging to this one, exposed, and often high-energy coast. The overwhelming impression of Panthalassa is one of scale, of simplicity, and of a profound, almost terrifying, emptiness. It was the vast, silent, blue counterpart to the vast, complex, rocky world of Pangea. It was the other half of the planet. And yet, this picture of a single ocean is not entirely complete. While Panthalassa was the great outer ocean, the sea shape of Pangea's landmass created another special body of water, a vast, sheltered bay tucked into the arms of the supercontinent. This was a sea with a different character entirely, a warm, tropical, and perhaps more vibrant world, known as the Tethys. If the great Panthalassa was the planet's vast, cold, and lonely outer courtyard, there was also an inner sanctuary, a different kind of sea, defined not by its infinite emptiness, but by its sheltered intimacy. We must look again at that strange sea shape of the supercontinent. The two great arms of Pangea, curving north and south, did not meet on the eastern side of the globe. They left a vast, open bay, a gigantic, crescent-shaped indentation in the side of the world. This was the Paleotethys Ocean. We call it an ocean, and it was certainly vast, larger than our modern Indian Ocean. But in the context of Pangea, it felt more like an immense, protected sea. Its waters were cradled in the arms of the supercontinent, shielded from the planet-spanning winds and the colossal, slow currents of the outer Panthalassa. This location was crucial. The Tethys Ocean was situated almost entirely within the warm, tropical latitudes of the globe. Imagine this sea. Its waters were not the cold, deep, churning abyss of the Panthalassic deep. They were warm, perhaps in places almost like a bath. They were sunlit and relatively shallow, at least around the edges. While the center of Panthalassa might have been a watery desert, starved of nutrients, the Tethys was the opposite. It was a crucible of life. The land masses of Pangea that surrounded it on three sides were in a constant state of slow erosion. Rivers, born in the mountains of the supercontinent, flowed down into this great inland sea, carrying a rich soup of minerals and sediments. In these warm, nutrient-rich, sun-drenched waters, life flourished. This was the ecological engine of the Permian world. The shallow continental shelves that lined the Tethys were perhaps the largest continuous stretch of tropical habitat the planet had ever known. They were home to vast, intricate reefs, built not by the corals we know today, but by strange extinct sponges, algae, and bryozoans. The seafloor was carpeted with shelled creatures, and the water column was filled with ammonites, ancient sharks, and bizarre fish. If the heart of Pangea was becoming a harsh and unforgiving desert, the Tethys Ocean was its vibrant, teeming, and colorful oasis. It was a sanctuary, a vast, warm, and gentle nursery where evolutionary experiments could unfold in relative peace. This sea, this great eastern bay, would become one of the most important features of the planet. It was a pocket of stability in a world of extremes. It was the biological reservoir that held the rich diversity of marine life. And tragically, it would also become a warm, stagnant trap when the planet's climate began to unravel. A story for later in our journey. But for now, picture this duality. The single vast continent, Pangea. The single vast outer ocean, Panthalassa. And tucked between them, this vibrant living heart, the warm blue Tethys Sea. With this geography now fixed in our minds, let us turn our attention away from the water and venture inland. Let us explore the continent itself, a new world defined not by gentle seas, but by a climate of profound continental scale extremes. Let us turn away now from the gentle, life-giving shores of the Tethys Sea. Our journey takes us inland, leaving the sound of the warm waves behind. We travel west, pushing deeper and deeper into the heart of the great supercontinent. And as we travel, the world changes. The air itself feels different. The soft, humid breath of the ocean begins to thin, fades, and is replaced by a profound, shimmering dryness. The green coastal forests become sparser, giving way to hardy scrublands, and then, eventually, to open, rocky plains. The sun feels hotter, more direct, more relentless. The sky perhaps seems a paler, dustier blue. We have entered a realm governed by a new, harsh and unforgiving set of rules. This is the secret of the Pangean climate, a secret born not of any external force, but of the continent's own impossible scale. Geologists have a simple word for this phenomenon: continentality. In our modern, fragmented world, no piece of land is truly impossibly far from an ocean. The great seas that cover 70% of our planet act as its thermal flywheel, its great stabilizing heart. Water is a magnificent reservoir of heat. It absorbs the sun's energy slowly, and it releases that energy just as slowly. This is why our coastlines are so often gentle, their temperatures moderated by the vast, steadying presence of the water. The ocean is our planet's buffer against extremes. But Pangea had almost no buffer. Pangea was the extreme. It was a single landmass so vast that its center, the land that would one day become parts of North America, Africa, and Europe, all crushed together, lay thousands upon thousands of kilometers from the nearest deep-water shore. Imagine a wind borne over the great Panthalassa. It is filled with moisture. It reaches the western coast of Pangea and begins its long journey inland. It rises over the coastal mountains, dropping its rain, nourishing a thin, green ribbon of life. But then it continues its journey eastward, across thousands of kilometers of rock and plain. By the time it reaches the deep interior, it has no more water to give. It is a dry, scorching, relentless wind, a wind that only takes moisture and never gives it back. Without the ocean's gentle, moderating blanket, the heart of Pangea was utterly at the mercy of the sun. When the Permian sun beat down upon this endless dry land, the rock and soil would heat up rapidly, ferociously. There was no water to absorb the energy, no moisture to evaporate and cool the air. The land would simply bake day after day, month after month, creating a scorching, continental-scale oven. The summers here were likely hotter than any summer we have ever experienced in human history. A sustained, suffocating, dry heat. And when the sun set, or when the long, dark winter arrived, the opposite was true. With no oceanic warmth to hold on to, that same land would radiate its heat back into the blackness of space with shocking speed. The nights would be bitterly, unnaturally cold. The winters, a deep and biting freeze. This was the fundamental law of the Pangean climate, a world of no moderation, a world of violent seasonal swings. It was a land of burning days and freezing nights, of scorching summers and frigid winters. This unforgiving cycle, this extreme continentality, was the engine that created the single most defining feature of Pangea's interior, a vast, silent, and almost lifeless emptiness, the greatest desert the Earth has ever known. So let us venture into this vast, empty heart. This was the great Pangean desert. We must immediately abandon our modern concept of a desert. The Sahara, the Gobi, the Atacama. These are vast and hostile, it is true, but they are mere provinces of dryness, fragments of aridity in a world of complex circulating weather. The desert at the heart of Pangea was of a different order entirely. It was not a desert, it was the desert, a single, continuous, hyper-arid zone that may have rivaled the entire continent of North America in size. It was a scar of absolute dryness born from the sheer impossible scale of the landmass itself. Imagine standing in its center, thousands of kilometers from the sound or smell of an ocean. The world here is painted in shades of red, orange, and ochre. The rocks are ancient, scoured bare, rich in iron that has slowly, dryly rusted under the Permian sun. The horizon, in every direction, is a shimmering, unbroken line of barren rock and endless shifting dunes. The sky above is not the deep, humid blue of our world. It is a pale, thin, metallic sky, bleached by the relentless sun and hazy with fine, suspended dust. Dust that never, ever settles. There is no green. There is no trace of standing water. There is only the land, the sky, and the profound, suffocating silence. During the long Pangean day, the sun was not a gentle source of warmth. It was an anvil. It was a physical weight. The dry, thin air offered no shield. The dark, iron-rich rock of the desert floor would absorb this energy relentlessly until the ground itself became a searing griddle, far too hot for any complex creature to touch. The air would shimmer, not with moisture, but with the sheer visible waves of heat rising from the baked earth. Any water from a storm that might have miraculously strayed inland a season ago would not form a puddle. It would have vanished, evaporated back into the dry air in a matter of minutes, leaving behind only the glittering, sterile white of salt flats, great crystallized plains that stretched for miles. There was no shade to be found, no oases. There was only the relentless, oppressive, baking heat. And then the sun would touch the hazy western horizon, and the heat would not fade gently. It would vanish as if a switch had been thrown. The same thin, dry air that offered no shield from the sun offered no blanket for the night. The land would radiate its immense thermal energy back into the blackness of space with terrifying speed. The temperature would plummet by 50, 60, perhaps even 70 degrees Celsius. The same rocks that would blister the skin at noon would now crack and shatter in the profound, sub-zero cold. The desert would groan, contracting in the freeze. This was not a place of gentle seasons. It was a place of daily, violent extremes, a relentless cycle of fire and ice, every 24 hours. And through it all, there was the wind. This was the only constant movement in the heart of Pangea. A constant, dry, abrasive wind, born from the immense temperature difference between the scorching interior and the distant, cool Panthalassa. This wind was not a life-bringer. It carried no moisture, no promise of rain. It carried only sand and dust. For millions of years, this wind was the only sculptor of the deep interior. It carved the mountains into strange, sharp-edged monuments. It moved colossal seas of sand, dune by dune, in a slow, unstoppable march across the empty plains. The sound of this wind, the sound of grit scouring rock, was perhaps the only sound. The silence here would have been absolute. No rustle of leaves, no call of birds, no buzz of insects. The great, active creatures of the Permian, the tusked herbivores, the saber-toothed hunters, they could not survive here. They were confined to the fringes, the thin, green, livable ribbons of land near the coasts, thousands of kilometers away. The deep interior was a void, a vast, sterile, beautiful and terrifying monument to the power of the planet's own unforgiving physics. This was the great dead heart of the supercontinent. But Pangaea was not all desert. Its climate was a story of two brutal opposing forces. While the interior baked and froze in stillness, the coastlines were drowning in violence. Let us leave the dry, static, silent heart of the continent behind and journey back thousands of kilometers to its edge. We return to the single great shoreline of Pangaea, the boundary between the baked land and the vast, endless Panthalassa. Here, the rules of the world were written not by stillness, but by a profound and devastating seasonal violence. The same force that created the interior desert, the extreme continentality of the land, created a monster on its coasts. This was the Pangean mega-monsoon. We must understand the engine that drove this weather. It was an engine of almost unimaginable scale, powered by the fundamental difference between rock and water. During the long Pangean winter, the colossal landmass, with no oceans to moderate it, would lose its heat to space and become intensely cold. This vast, frigid continent would chill the air above it, creating a massive, stable dome of high pressure. The winds, pushed by this high pressure, would flow outward, away from the land, sweeping across the coasts and out into the comparatively warmer ocean. For half the year, the coasts of Pangaea were locked in a dry, cool and relentless offshore wind. The land would dry out, the rivers would shrink, and all of life would wait, in a state of suspended, thirsty anticipation. And then, the season would turn. The sun would begin to climb higher, its rays striking the immense exposed rock of the interior, and that vast, dark landmass would begin to heat up. Not slowly, like the ocean, but rapidly, ferociously. The heart of Pangaea would become a planetary-scale blast furnace, a continent-sized oven baking under the sun. This superheated land heated the air above it, causing it to rise, creating a colossal, continent-spanning zone of low pressure. A vacuum sucking the air upwards. The planet's atmosphere, which abhors a vacuum, had to respond. Far out at sea, the great Panthalassa Ocean, with its immense thermal mass, had barely changed temperature. It remained cool, stable, and its surface air was heavy with moisture, evaporated over tens of thousands of kilometers of open water. And so, the great wind reversed. The planet took a breath. The cool, heavy, moisture-saturated air of the ocean was pulled irresistibly toward the gaping, low-pressure void in the heart of the continent. This was not a gentle sea breeze. This was an invasion. Imagine standing on the Pangean coast as this seasonal shift occurred. The air, for months dry and blowing from the land, would still, and then a new wind would begin, a steady, humid push from the ocean. Day by day, it would grow in strength. On the horizon, clouds would begin to gather. Not the scattered, puffy clouds of our world, but a vast, dark, unified wall of moisture, a towering battlement of deep grey and blue, stretching from one end of the horizon to the other. When this wall of moisture hit the hot land, it was not a gentle rain. It was a deluge. It was a seasonal apocalypse. The sky would break open. The rain would fall not as drops, but as a solid, roaring curtain of water, a sound so loud it would drown out all other thought. This rain would last not for an hour or a day. It would last for months. The parched land, baked hard by the long dry season, could not absorb this sudden flood. The water would instantly transform the landscape. Dry riverbeds, known as wadis, which had been dusty, empty canyons for half the year, would fill in an instant, a terrifying, debris-filled, roaring torrent of brown water. Sheet floods would scour the plains, stripping away soil, carving new channels in the rock. This was the rhythm of Pangean coastal life. a life of extremes, 6 months of desperate drought, followed by 6 months of catastrophic flood. This seasonal violence was the great defining force for every living thing that did not inhabit the deep desert. The forests, the herbivores, the predators, their entire life cycle was dictated by this boom and bust of water. They had to endure the drought, and they had to survive the flood. This world of fire and water, of dry hearts and violent coasts, was extreme enough. But Pangea held one more climatic secret. Its vast size meant that it did not just span the equator. It stretched all the way to the ends of the Earth. It touched the poles. This supercontinent was so vast, its climate was a story of warring extremes. We have felt the dry, static heat of its interior, and we have listened to the violent, seasonal roar of its monsoonal coasts. But Pangea was a landmass of such impossible scale that it was not defined only by heat. It stretched from one end of the Earth to the other, and because of this, it was also a world of profound and enduring cold. Let us journey south, far south. Past the Great Desert, past the zone of the monsoons, we travel toward the bottom of the world. In our modern geography, the South Pole is a continent, Antarctica, an island of ice, isolated and alone. But in the age of Pangea, the South Pole was not an island, it was simply a location within the supercontinent. The great southern mass of Gondwana, the land that would one day become Antarctica, Australia, Southern Africa, and the tip of South America, was physically sitting over the planet's southern axis. And it was cold. During the Permian, the Earth was not, on average, a frozen planet. But a landmass at the pole will always gather ice. Here, in the far south of Pangea, lay a vast polar ice cap. Not sea ice, but a true continental glacier, perhaps miles thick in its center, an immense, heavy shield of white resting upon the land itself. Imagine this landscape, an endless white desert of ice stretching for thousands of kilometers, burying the future mountains and valleys of Antarctica under a silent, frozen mass. The true character of this land, however, was defined not just by the cold, but by the darkness. Here, at the bottom of the world, the sun was a fleeting visitor. For 6 months of the year, this entire region was plunged into the profound, unbroken twilight and darkness of the polar night. The silence here would have been of a different kind than the deserts. It was the deep, muffled silence of snow. The only sound would be the wind, a wind that had never known warmth, sweeping across the ice sheet, and beneath, the slow tectonic groan and crack of the ice sheets themselves, grinding the rock of the continent hidden below. Life, you would think, could not exist here, and on the ice cap itself, it likely did not. But on the fringes of this great southern glacier, on the land that would one day be South Africa or Australia, life was holding on. This was not the vibrant, easy life of the Tethys. This was a life of endurance. Hardy, resilient forests, a kind we will explore later, learned to survive this. They learned to grow in the thin, rocky soil at the glacier's edge, to endure the biting cold, and to wait, dormant and silent, through the 6 long months of darkness, hoping for the sun's brief, low-angled return. But the planet was not symmetrical. If we travel to the opposite end of the globe, to the North Pole, we find a different scene. The landmass of Pangea did not quite reach the top of the world. The northernmost part of the continent, the land that would be Siberia, sat in the high northern latitudes, but the pole itself was likely open ocean, part of the Great Panthalassa. So the world of Pangea had 2 poles of a different nature, a vast, frozen, land-based ice cap in the south, and a cold, perhaps misty, but likely ice-free sea in the north, bordered by dark, temperate forests. This, then, was the complete picture of the Pangean world. A planet of impossible contrasts. A scorching, sterile desert at its heart. violent, flood-prone monsoons on its coasts, and a vast, silent desert of ice at its southern end. It was a world of harsh, uncompromising environments, and the air that blew across these lands, the very atmosphere connecting them, held its own ancient secret, a secret of abundant life and abundant danger. This then was Pangea, a single sprawling world of impossible contrasts, a scorching sterile desert at its heart, violent flood-prone monsoons on its coasts, and a vast silent desert of ice at its southern end. These realms, though seemingly separate in their character, were all united. They were all connected by one single shared envelope, the atmosphere, the Pangean sky. So let us pause for a moment and ask a simple question. What was it like to breathe? If you were to stand on a Pangean shore, surrounded by the strange alien forests, what would the air itself have felt like? The air of the Permian, especially the early Permian when Pangea was young, was a direct inheritance from the age that had come just before, the Carboniferous. The Carboniferous period was the great age of coal. For 30 million years, the fragmented tropical continents that existed before Pangea were covered in vast, steaming, swampy forests. These were not the forests we know. They were forests of towering fern-like trees, giant club mosses, and colossal horsetails. And for millions of years, these forests lived, died, and fell into the stagnant, oxygen-poor water of the swamps. They did not decay, not in the way our forests do. They were simply buried, layer upon layer, their bodies locking away billions of tons of carbon deep within the earth. But as these forests grew, as they drank in the sunlight, they were doing something else. Through the relentless planetary scale engine of photosynthesis, they were breathing out, and they were breathing out oxygen. For millions of years, they pumped this waste gas into the sky. And because the carbon of their bodies was being buried, not decaying and consuming oxygen to rot, this oxygen had nowhere to go. It simply accumulated. The atmosphere that Pangea inherited was therefore unlike our own. It was an atmosphere supercharged. In our modern world, the air is about 21% oxygen. In the late Carboniferous and early Permian, that number may have reached 30, perhaps even 35%. What would this feel like? This air would have been denser, heavier. You would feel its pressure on your skin in a way we do not. To take a breath, to draw this thick, rich air into your lungs, would be an entirely different sensation. It would be effortless. Each breath would deliver a rush of fuel to your blood, a feeling of vibrant energy, perhaps even a strange, dizzying lightness. The world would have seemed sharper. Smells would travel further, carried more efficiently by the denser air. Sounds, too, would be different. But this oxygen-rich world held a dark and dangerous secret. It was a tinderbox. Fire, in a world of 35% oxygen, is not the fire we know. It is a creature of explosive, ravenous violence. A damp leaf, which in our world would smolder and go out, would in that world burst into flame. A spark from a falling rock, a flash of lightning from a monsoonal storm. These were not small events. They were catastrophes. Lightning strikes would have been apocalyptic, triggering firestorms that would sweep across the land with terrifying speed, consuming everything in their path. The air of the Permian, especially near the forests, would have carried a constant, sharp, electrical smell, the smell of ozone, and almost always the distant, resinous tang of smoke. This was the air of Pangea, rich, energetic, and explosive. And this volatile, supercharged atmosphere was not just a curiosity, it was an engine. It was the fuel that allowed for a very specific and very strange kind of life to exist. A kind of life that, in our modern, thinner air, is no longer possible. This was the secret that powered the last days of the true giants, the giants of the insect world. This rich, dense, and volatile atmosphere was more than just a chemical curiosity. It was an evolutionary force. It was a biological enabler. It solved a problem that, in our modern world, puts a firm and final limit on the size of an entire class of life. Today, the creatures that dominate the small spaces of our world, the insects, the spiders, the millipedes, are held captive by the air itself. They do not breathe as we do. They have no lungs, no complex circulatory system to pump oxygen-rich blood through their bodies. Instead, they rely on a far simpler, more ancient system, a network of tiny, hollow tubes called tracheae that run from small openings on their exterior deep into their tissues. They breathe through passive diffusion. Oxygen from the air must travel on its own down these long, branching, microscopic tunnels to reach the cells that need it. In our modern 21% oxygen world, this system is a profound limitation. It is only efficient over very, very short distances. If an insect were to grow as large as a dog, the oxygen simply could not diffuse fast enough or deep enough to power its body. Its inner cells would suffocate. This, more than any other reason, is why our insects are small. But the air of the early Permian was not our air. In a world of 30 or 35% oxygen, the rules were different. The very concentration of the gas in the atmosphere created a powerful passive pressure. Oxygen in this supercharged air could be pushed much deeper, much more efficiently down those same simple tubes. The old limitations were shattered. The passive breathing system that now restricts insects, then it empowered them. And so, the world of Pangea, at least in its wetter, forested regions, was home to the last of the true giants, the megafauna of the arthropod world. Let us try to picture this. Imagine standing in one of the vast fern-covered lowlands near the coast in the humid, oxygen-thick air. You hear a sound. Not a chirp, not a buzz, but a deep, rhythmic, leathery thrumming. A shadow passes over you, as large as the shadow of a hawk. You look up, and you see Meganeura. This was not a dragonfly. This was a griffinfly, a creature that resembled its modern cousins in almost every way except for its scale. Its wingspan was not measured in centimeters, but in feet. 70 centimeters, 2.5 feet across. The largest flying insect that has ever lived. It would have been a terrifying and beautiful sight, its iridescent wings beating the thick air, its large alien eyes scanning for prey. It was the apex predator of the Pangean sky, a sky that belonged not to birds, which had not yet evolved, but to these. And on the forest floor, beneath the giant 30-meter-tall tree ferns, something else is moving. It is not moving quickly. It is moving with a slow, tank-like, inevitable power. This is Arthropleura. Imagine a millipede. Now imagine it as long as a small car and as wide as a man. 2.5 meters, or 8 feet, long. It is the largest land-dwelling invertebrate of all time. Its great armored, segmented body, perhaps 1.5 feet wide, pushes through the damp leaf litter. It is not a hunter. It is a slow, methodical herbivore, its hundreds of legs moving in a silent, hypnotic ripple as it navigates the fallen logs and giant fungi of the forest floor. Its passage would not be silent. It would be the sound of a living, armored train, the rustling and cracking of vegetation under its immense, distributed weight. This was the world made possible by that thick, volatile air. A world where scorpions could grow to the length of a human forearm, and where other, stranger creatures patrolled the undergrowth. But this was not a world destined to last. It was a holdover, a magnificent echo of the Carboniferous swamps. As Pangea truly coalesced, as the climate began its long, slow march toward aridity, the great coal swamps began to shrink. The forests, the great engines of oxygen, were in slow decline. The air itself was beginning to thin. The reign of the giant insects was already coming to an end. They were the last spectacular expression of a high-oxygen Earth. Their slow, inevitable decline as the planet's atmosphere changed was a quiet, early warning. It was a sign that the world of Pangaea was changing, becoming harsher, and paving the way for a new and very different dynasty of creatures. Creatures that had evolved a far more efficient way to breathe and were ready to conquer this new, harder continent. The thick, oxygen-rich air that had fueled the brief, spectacular reign of the giant arthropods was beginning to thin. The great coal swamps of the Carboniferous, those vast planetary-scale oxygen factories, were in a slow, irreversible decline. Pangaea was assembling, and as it assembled, the climate became drier. The swamps retreated, and the world's atmosphere began its long, slow return to a more stable, less volatile state. This new, harder world, the world of Pangaea, demanded a new kind of ruler. It demanded creatures that were not reliant on the passive, inefficient breathing of insects. It demanded creatures that were not, like the amphibians, still chained to the dwindling ponds and rivers, needing to keep their skin moist. It demanded a new kind of animal, one that had truly, fully, and finally conquered the land, one that could withstand the dryness, the heat, and the cold. And in this new world, one group rose to meet the challenge. They were not dinosaurs. The first dinosaurs were still tens of millions of years in the future, small, shadowy creatures biding their time. They were not yet true reptiles, as we know them. They were something else entirely, something stranger, and something far closer to us. We call them the Synapsids. This name may sound academic, but its meaning is simple, and it is profound. When the first four-legged animals left the water, the great tree of life split into two main branches. One branch, the Sauropsids, would eventually lead to all the creatures we think of as reptiles: the lizards, the crocodiles, the great marine plesiosaurs, the pterodactyls, and eventually the dinosaurs and the birds. But the other branch, that was the Synapsid branch. This was our branch. These were the creatures that, after a long, winding, and perilous journey through time, would eventually, millions of years later, give rise to the first true mammals, to us. So, as we journey into the heart of the Permian, as we explore the world of Pangaea, we are not looking at a world of alien lizards. We are looking at our own, distant, forgotten family. We are witnessing the first great evolutionary experiment in what it means to be a mammal. This was their time. This was the age of synapsids. For nearly 60 million years, they were the undisputed masters of the planet, and they were a bizarre and wondrous menagerie. They were not the slow, sprawling, cold-blooded creatures we might imagine. They were pioneers. They were experimenting with new ways of living. Many of them were active, powerful animals. They were developing more efficient lungs. They were evolving differentiated teeth, incisors for nipping, canines for tearing, molars for grinding, something no reptile has ever truly achieved. And, perhaps most importantly, they were experimenting with warm-bloodedness. In the harsh, unforgiving climate of Pangaea, with its scorching days and its freezing nights, this was the ultimate evolutionary advantage. A creature that could generate its own internal heat, a creature that could regulate its own body temperature, was not a slave to the sun. It could hunt in the cool of the morning. It could remain active in the chill of the night. It could survive the seasonal extremes that would send a cold-blooded amphibian or reptile into a state of helpless torpor. These were the creatures that truly inherited the supercontinent. They came in all shapes and sizes. There were stout, barrel-bodied herbivores that roamed the land in vast herds, a preview of the wildebeest or bison to come. There were giants armored in thick, bony plates, and there were the hunters. The first great saber-toothed predators to ever walk the earth belonged to this dynasty. To understand this forgotten age, this first great reign of our own lineage, We must begin at the beginning of their dominance. We must meet the creature that has become the icon of this lost world, a strange, powerful hunter, famous not for its teeth, but for the magnificent, terrifying, and utterly mysterious sail that it wore upon its back. Let us travel back now to the early Permian, roughly 290 million years ago. Pangea is newly formed. The great mountain ranges are still young and jagged. The climate is beginning its long shift toward dryness, but the oxygen-rich legacy of the Carboniferous still lingers in the air. The vast coal swamps are retreating, replaced by drier fern prairies and coniferous woodlands. And stalking through this ancient landscape is the creature that, for many, defines this lost world. Dimetrodon. Picture it now, it is not a dinosaur. It arrived on the scene, reigned, and vanished tens of millions of years before the first true dinosaurs would appear. It is something older, something closer to us. It is a synapsid, a mammal-like reptile. Imagine a creature the size of a large crocodile, perhaps 3 meters or 10 feet long. Its body is low-slung, powerful, with sturdy legs sprawled slightly out to the sides in a more reptilian posture, not held directly beneath the body like a mammal or a dinosaur. Its tail is long and heavy. Its head is massive, deep-skulled, with powerful jaws. And within those jaws lies a clue to its identity, a sign of its synapsid heritage. The teeth are not the simple uniform pegs of a typical reptile. They are differentiated. There are sharp, stabbing teeth at the front, incisors and large dagger-like canines, and smaller shearing teeth further back. This is the toolkit of a specialized predator designed for seizing, killing, and perhaps even roughly processing its prey. Dimetrodon was undoubtedly one of the apex hunters of its time, likely preying upon the large amphibians, the early reptiles, and even other smaller synapsids that shared its world. But all of this, its size, its teeth, its powerful build, is utterly overshadowed by the one feature that makes Dimetrodon instantly recognizable, the feature that has puzzled and fascinated scientists for over a century. Rising from its back, like a great macabre billboard, is an immense sail. This structure is formed by incredibly elongated neural spines, bony rods growing directly upwards from each vertebra of its backbone, reaching perhaps 1.5 meters, 5 feet, tall at their peak. In life, these spines were almost certainly connected by a thin, delicate membrane of skin, richly supplied with blood vessels. Imagine this creature moving through the Permian landscape. That huge, stiff sail, perhaps brightly colored, perhaps patterned, would have been an unavoidable, almost unbelievable sight. What on earth was it for? This remains one of the great mysteries of the deep past. For many years, the leading hypothesis was thermoregulation. The Pangean climate, as we know, was one of harsh extremes. Perhaps this giant sail acted like a biological radiator or a solar panel. In the cool Permian mornings, Dimetrodon could turn its sail broadside to the rising sun. The vast surface area, filled with blood vessels, would rapidly absorb the solar heat, warming its body much faster than a creature without such a structure. This would give it a crucial advantage, allowing it to become active, ready to hunt, while its cold-blooded prey were still sluggish and slow. Conversely, if the creature became too hot under the relentless Pangean sun, it could turn its sail edge-on to the sun, or seek a breeze. The same large surface area could then radiate excess heat away, helping it to cool down. It was an elegant idea, a biological thermostat perfectly suited to a world of temperature swings. But doubts remain. Would such a delicate, exposed structure so vital for survival be too vulnerable to damage? Would the warming and cooling process actually be fast enough to provide a significant advantage? More recently, another hypothesis has gained favor: display. Perhaps the sail wasn't primarily about heat, but about communication. Perhaps it was a giant billboard used for sexual selection, with males sporting larger, more colourful sails to attract mates, like the antlers of a modern deer or the tail of a peacock. Or perhaps it was used for species recognition, helping different types of sail-backed synapsids tell each other apart. Or maybe it was simply an intimidation device, making the creature look even larger and more formidable to rivals or potential prey. The truth may lie somewhere in between, a combination of display and perhaps some secondary thermoregulatory benefit. We may never know for sure. The sail remains an enigma, a silent, stony question mark rising from the deep past. But whatever its function, it defines Dimetrodon. It makes this early predator, this distant relative on our own family tree, an unforgettable icon of a lost world. It is a reminder that evolution, in its endless experimentation, sometimes produces solutions that are as bizarre and beautiful as they are mysterious. Dimetrodon eventually faded, replaced by other, perhaps more advanced, synapsid predators. But its sail stands as a monument to the first great age when creatures like us, or at least creatures leading to us, ruled the earth. And its prey, the vast herds that sustained it, were perhaps even stranger. If Dimetrodon, with its fearsome teeth and enigmatic sail, represented the predatory edge of the early Permian world, the vast, beating heart of that ecosystem belonged to a different group entirely. These were the creatures that truly defined the landscape through their sheer, overwhelming numbers. They were the great herbivores of their age, the grazers and browsers that converted the tough Permian vegetation into flesh, forming the broad, stable base of the food pyramid upon which the hunters depended. They too were synapsids, our distant relatives. But they had taken a radically different evolutionary path. Forget the sharp teeth and the intimidating sails. These were creatures built for bulk, for endurance, and for the relentless, patient processing of plants. We call them the Dicynodonts. The name means two dog teeth, referring to the prominent tusks that many, though not all, possessed. Let us try to picture them now, perhaps wandering across the fern prairies or moving through the open woodlands of Glossopteris trees in the slightly cooler, wetter regions nearer the Pangean coasts or in the southern latitudes. These were not graceful creatures. They were built like walking barrels. Their bodies were stout, immensely powerful, with deep chests and broad, sturdy hips. Their legs were short, thick pillars, perhaps held in a semi-sprawling gait, suggesting not speed, but immense strength and stability. Their heads were often large, blunt, and seemingly truncated, ending not in a mouth full of varied teeth, but in a horny, turtle-like beak. This beak was a powerful tool, perfectly adapted for shearing off tough, fibrous stems, roots, and leaves. Behind this beak, inside the mouth, they likely possessed rough, bony plates on the palate and lower jaw, used for grinding and crushing this coarse vegetation before swallowing. And jutting down from the upper jaw in many species were those defining tusks. These varied greatly in size and shape. Some were small, almost vestigial. Others were enormous, curving downwards like the tusks of a modern walrus. Their function remains debated. Were they defensive weapons against predators like the Gorgonopsians? Were they used for digging up nutritious roots and tubers from the dry Pangean soil? Or were they primarily for display, perhaps used by males in ritual combat for dominance or mates? Likely they served a combination of these roles, versatile tools in a challenging world. Imagine seeing not just one, but herds of these creatures. Dicynodonts were incredibly successful. Their fossils are found in staggering numbers across the globe, on every part of the Pangea landmass where life could find a foothold. They came in a vast array of sizes. Some were as small as modern rabbits, perhaps living in burrows to escape the heat and predators. Others, like the later Plaxerias, reached the size of a hippopotamus, weighing several tons, true mega-herbivores shaping their environment through sheer bulk and relentless feeding. Picture a herd of medium-sized dicynodonts, perhaps creatures like Diictodon or Udenodon, moving slowly across the landscape. They are low-slung, their beaked heads methodically cropping the low-growing vegetation. Their tough hides, perhaps sparsely covered in bristle-like hairs, offer some protection from the sun and from biting insects. They move with a slow, ponderous gait, their short legs carrying their immense weight. Occasionally, one might use its tusks to root in the earth, searching for something more substantial. Their presence would have defined the soundscape of the habitable parts of Pangaea. Not the sharp calls of birds, but perhaps the low grunts and bellows of these great herbivores communicating within the herd. The constant, rhythmic sound of their beaks shearing vegetation, the heavy thud of their footsteps on the dry earth. They were the ecological equivalent of the vast herds of wildebeest on the Serengeti today, or perhaps the bison that once dominated North America. They were the primary consumers, the great lawnmowers of the Permian, converting plant matter into animal protein on an industrial scale. Their sheer numbers, their constant feeding, would have profoundly shaped the plant communities, preventing forests from completely taking over in some areas, maintaining open woodlands and prairies through their grazing pressure. And their abundance made them the primary food source for the predators of their time. The story of Permian land life is, in many ways, the story of the relationship between the dicynodonts and the creatures that hunted them. These strange, tusked, beaked, barrel-bodied synapsids were a triumph of evolutionary design, perfectly adapted to the challenges of Pangaea. They were resilient, widespread, and ecologically dominant for tens of millions of years. They were the quiet, unassuming, yet utterly foundational pillars of this lost ecosystem. Their reign seems, from our distant perspective, stable, almost eternal. But even these masters of herbivory were living on borrowed time, unaware of the planetary catastrophe that was slowly gathering force, a catastrophe that would ultimately bring their long, successful dynasty crashing down, along with almost everything else. But before that darkness fell, they shared the world with other giants, creatures built not like barrels, but like fortresses. While the dicynodonts, those tusked and barrel-bodied synapsids, represented the dominant line of large herbivores across Pangaea, they were not entirely alone in their niche. Sharing the landscape, particularly perhaps in the wetter regions nearer the coasts or along the great river systems that dissected the continent, was another group of giants. These were creatures built on an entirely different plan, belonging not to our own synapsid lineage, but representing a strange, early, and ultimately doomed branch closer to the true reptiles. These were the Periasaurs. Imagine a creature that seems less like an animal and more like a walking fortress. If the dicynodonts were the hippos or rhinos of their day, the Periasaurs were perhaps the armored glyptodonts, or maybe even stranger, reptilian tanks covered in bony armor. Picture Scutosaurus, one of the best-known members of this group. It was immense, reaching lengths of up to 3 meters, or 10 feet, and built with incredible robustness. Its body was broad, deep, almost ridiculously wide, supported by short, stout, pillar-like legs held somewhat awkwardly beneath its bulk. It was clearly not built for speed, but for sheer, immovable presence. Its head was relatively small, boxy, perhaps with simple peg-like teeth designed for cropping soft vegetation. But the skull itself was extraordinary, adorned with bizarre bony knobs, flanges, and bosses projecting outwards, particularly around the cheeks and the back of the head. It looked almost like a gargoyle carved from stone. And its body was its shield. Unlike the synapsids, which relied perhaps on thick hides or simply their size for protection, the Periasaurs had taken a different route. Their skin was studded with thousands of small bony plates called osteoderms embedded directly within the dermis, forming a flexible yet incredibly tough coat of mail beneath the outer layer of skin. This wasn't a solid shell like a turtle's, but a dense, all-encompassing armor offering protection against the bites and claws of predators from almost any angle. To see a pariasaur moving through the Permian landscape would be to witness a living battleship. Slow, ponderous, seemingly invulnerable. They likely browsed on softer, perhaps semi-aquatic vegetation, their simple teeth ill-suited for the truly tough, fibrous plants that the beaked dicynodonts could handle. Some evidence even suggests they may have spent considerable time in or near water, like modern hippos, using the buoyancy to support their immense weight and perhaps finding refuge from the Pangean heat and predators. Their defense against hunters like the Gorgonopsians was likely passive. They could not outrun them. They could not likely outfight them. Their strategy was simply to endure, to rely on their immense bulk and their all-encompassing armor to make them too difficult, too costly a meal for even the most determined predator to tackle easily. Imagine a Gorgonopsian attempting to bite through that thick, bony hide. It would be like trying to chew through chainmail. The pariasaurs represent a fascinating evolutionary experiment. They were para-reptiles, an early offshoot from the main reptilian line, cousins perhaps to turtles, but not directly ancestral to any living group. They achieved immense size and ecological importance during the Permian, coexisting alongside the dominant synapsid herbivores, perhaps exploiting slightly different food sources or habitats. Their presence adds another layer of strangeness and grandeur to this lost world. They were the lumbering, armored giants, the living tanks that browsed the wetter edges of Pangea, their bizarre knobbed heads low to the ground, their bony hides impervious to almost everything except the slow passage of time and the coming catastrophic fire. They stand as a reminder that evolution explores many paths, creates many forms of success, not all of which are destined to lead to the familiar creatures of our modern world. They were another magnificent but ultimately temporary dynasty that ruled before the rise of the dinosaurs. And ruling above them all, at the absolute apex of this complex food web, was the true terror of the Permian night. The age of Pangea was a world ruled by giants. We have met the strange, tusked herbivores, the dicynodonts that covered the plains in their millions. We have seen the armored, slow-moving fortresses, the pariasaurs that browsed the wetter lowlands. And we encountered the early sail-backed hunter, Dimetrodon, that defined the dawn of this era. But as the Permian period wore on, as Pangea matured and perhaps grew even harsher, a new and far more terrifying predator rose to prominence. The reign of Dimetrodon faded, its lineage dwindled, and taking its place at the absolute apex of the terrestrial food web was a creature that embodied the predatory power of this Synapsid dynasty pushed to its brutal extreme. These were the Gorgonopsians. Let us try to conjure their image now, perhaps stalking silently through the twilight of a late Permian evening 260 million years ago. Forget the sprawling gait of Dimetrodon. The Gorgonopsians were built differently. They were among the first creatures on Earth to evolve a more upright posture. Their powerful legs held more directly beneath their bodies, not splayed out to the sides. This was a revolutionary development. It allowed for greater efficiency, greater stamina, and potentially greater speed. These were not slow, lumbering ambush hunters. These were active, powerful pursuers. Imagine a creature built perhaps like a cross between a great wolf and a saber-toothed cat, but reptilian in its essence, yet fundamentally not a reptile. Sizes varied within the group, but the largest, creatures like Inostrancevia, found in what is now Russia, reached the size of a large bear, perhaps 3.5 meters, or nearly 12 feet, long and powerfully built. Their heads were immense, deep, and terrifyingly armed. The skull was elongated but reinforced, designed to withstand immense stress. The jaws were incredibly powerful, capable of delivering a devastating bite. But it was the teeth that truly defined them. Like Dimetrodon, they possessed differentiated teeth, a hallmark of their Synapsid lineage. But in the Gorgonopsians, this specialization reached a new, terrifying peak. At the front of the upper jaw, flanking perhaps smaller incisors, grew two enormous dagger-like canine teeth. These were not merely large, they were sabers, flattened side to side, perhaps serrated along their edges, extending far below the lower jaw even when the mouth was closed. They were weapons clearly designed not just for puncturing hide, but for inflicting deep, catastrophic wounds, for slicing through muscle and finding major blood vessels. They were the teeth of a killer specialized in tackling prey as large, or perhaps even larger than itself. Picture this creature moving. Its powerful pillar-like legs carry its muscular body with a surprisingly fluid, perhaps almost mammalian gait. Its senses are likely sharp. Large eye sockets suggest good vision, perhaps adapted for hunting in the lower light of dawn and dusk. Openings in the skull hint at a keen sense of smell, allowing it to track its prey, likely the vast herds of dicynodonts across the dry Pangean plains. Its skin. We do not know for sure. Was it scaled like a reptile, or did it possess the beginnings of something else? Perhaps a tough, leathery hide, perhaps even patches of sparse, bristle-like hair, an early experiment in insulation, hinting at the warm-blooded future of its distant descendants. The fossils are silent on this, leaving it to our imagination. But there is little doubt about its nature. The Gorgonopsian was the undisputed king of the late Permian world. It was the terror that haunted the dicynodont herds. Its presence would have instilled a constant, low-level fear in the landscape. The discovery of its tracks, or the chilling sight of its saber-toothed silhouette against the setting sun, would have sent waves of panic through any creature unfortunate enough to cross its path. Imagine the hunt, perhaps a solitary stalk through the sparse Glossopteris woodlands. The Gorgonopsian uses its keen senses to locate a herd of dicynodonts. It approaches slowly, using cover, its powerful muscles tensed. Then a sudden burst of speed, not the lightning dash of a cheetah perhaps, but a terrifying ground-shaking charge. It closes the distance, selects its target, perhaps a young, old or unwary individual, and then the final brutal attack. Those immense saber teeth plunge deep into the flank or neck of the prey. The struggle might be brief, or it might be a violent, dusty battle, but the outcome is rarely in doubt. The Gorgonopsians represent the peak of Synapsid predatory evolution before the Great Catastrophe. They were faster, perhaps smarter, and certainly more lethally armed than the predators that came before them. They were the wolves, the lions, the saber-toothed tigers of their age, all rolled into one magnificent, terrifying package. They were the final, glorious expression of this first great dynasty of creatures on our own evolutionary line, ruling Pangea with brutal efficiency, utterly unaware that their reign and the world they knew was poised on the brink of an unimaginable abyss. Their shadows stretched long across the Permian landscape, but an even darker shadow was beginning to fall from the sky itself. While the great Synapsid dynasties, the sail-backed hunters, the tusked herbivores, the saber-toothed predators, held center stage, playing out the grand dramas of life and death across the vast Pangean landscape, another story was unfolding quietly in the shadows. Another lineage, following a different evolutionary path, was patiently biding its time. These were the Sauropsids, the creatures belonging to the other great branch of four-legged life, the branch that would eventually give rise to the lizards, the snakes, the turtles, the crocodiles, and, most significantly for the future, the dinosaurs and the birds. In the Permian world, dominated by their Synapsid cousins, these early Sauropsids were largely secondary players. They were not the giants, they were not the apex predators. They were the understudies, the creatures living in the margins, experimenting with different ways of life, perhaps less spectacular, but ultimately incredibly resilient. Let us try to picture them now, sharing the same world as the mighty Gorgonopsians and the vast herds of Dicynodonts, but occupying different spaces, different niches. Many of them were likely small, agile creatures. Imagine lizard-like forms, perhaps resembling modern iguanas or monitors, but belonging to more ancient groups, darting through the undergrowth, hunting insects, or perhaps small amphibians. Creatures like Procolophon, small, stout-bodied herbivores with broad, simple teeth, might have browsed on low-growing vegetation, perhaps digging burrows for shelter, always wary of the larger synapsids that shared their world. These early reptiles possessed certain advantages that would prove crucial in the long run. Their scales offered excellent protection against the drying Pangean air, perhaps better than the potentially less protected hides of some synapsids. Their metabolism was likely slower, more classically cold-blooded. While this made them less active, less capable of sustained bursts of energy compared to the potentially warm-blooded synapsids, it also meant they needed less food, less fuel to simply survive. In a harsh world prone to drought and famine, this lower energy demand could be a powerful advantage. They could wait out the hard times, conserving energy, while their high metabolism synapsid neighbors starved. And they were experimenting with different ways of moving. While the synapsids were evolving more upright, efficient postures, some sauropsid lineages were exploring other possibilities. Early archosauromorphs, the group that would eventually include crocodiles and dinosaurs, were perhaps already showing hints of the anatomical changes that would lead to bipedalism, running efficiently on two legs, a trait that would become a defining feature of the dinosaurs millions of years later. Imagine small, swift creatures, perhaps capable of brief bursts of two-legged running to escape danger or snatch prey, a fleeting preview of the speed and agility that would one day conquer the world. Some sauropsids even returned to the water. Creatures like Hovasaurus, found in what is now Madagascar, developed flattened tails for propulsion, becoming adept swimmers in the freshwater lakes and rivers of Pangea, perhaps hunting fish or amphibians, finding refuge from the harshness of the land beneath the surface. These early sauropsids were diverse, adaptable, and persistent. They were not yet challenging the synapsids for dominance. They occupied the smaller niches, the less desirable roles in the ecosystem. They were the supporting cast in a play dominated by another family. But they possessed a hidden potential. Their efficient water conservation, their lower energy needs, and their capacity for evolutionary innovation, particularly in locomotion, were traits perfectly suited for the world that was coming. They were, perhaps without knowing it, pre-adapted for survival in the face of catastrophe. When the great firestorm eventually broke, when the world collapsed, when the mighty Synapsid dynasties that had ruled for 60 million years were decimated, these humble creatures hiding in the shadows, these patient survivors, would inherit the earth. Their story during the Permian is one of quiet endurance. It is a reminder that dominance is often temporary, that the future belongs not always to the strongest or the largest, but sometimes to the most adaptable, the most resilient, the ones who can weather the storm when the giants fall. The age of reptiles was still far off, but its seeds were being sown here, silently, persistently, in the dusty soil of Pangea, under the watchful, indifferent eyes of the Synapsid kings. While the great animal dynasties played out their dramas of predator and prey across the vast stage of Pangea, the stage itself was set by a silent green kingdom, the plants. The flora of Pangea was as unique and distinct as its fauna, shaped by the same forces of a unified world, a harsh climate, and the relentless passage of deep time. The lush, steaming, globally uniform swamp forests of the Carboniferous, the age that came before, were largely gone. Pangaea demanded something tougher, something more resilient, and in the vast southern expanses of the supercontinent, the landmass of Gondwana, stretching down towards the icy South Pole, one group of plants rose to define the landscape. This was the age of the Glossopterids, and specifically the tree that gives the group its name, Glossopteris. Let us try to picture these lost forests. Forget the towering feathery tree ferns and giant club mosses of the coal swamps. Forget the familiar broad leaves of modern deciduous forests or the dense needles of pine woods. The Glossopteris forests were something else entirely. Imagine trees perhaps reaching respectable heights, maybe 10 or 20 meters tall, forming extensive open woodlands rather than dense closed canopies. Their most distinctive feature was their leaves. Glossopteris literally means tongue fern, and their leaves were precisely that, long, simple, tongue-shaped or strap-shaped, perhaps somewhat thick and leathery, with a prominent central midrib and a network of branching veins. They were not delicate, fluttering leaves. They were likely tough, adapted to withstand dry seasons, perhaps even periods of cold near the southern polar regions. They grew not scattered along branches, but perhaps in dense clusters, almost like whorls at the ends of stout twigs. These forests would have stretched for immense distances across the southern plains and hillsides of Pangaea, across future Antarctica, Australia, India, South America, and Africa, all then locked together. Finding Glossopteris fossils on all these now separated continents was, in fact, one of the key pieces of evidence that Alfred Wegener used to first propose the radical idea of continental drift, the idea of Pangaea itself. These fossil leaves became the silent, stony proof of a once unified world. What would it feel like to walk through such a forest? Perhaps quieter, more open than the forests we know. The understory beneath the Glossopteris trees might have been sparse, dominated by hardier ferns, seed ferns, and perhaps early cycads, adapted to the drier conditions and the seasonal light. The air would carry the scent of dry earth, perhaps a faint resinous tang from the trees themselves, different from the damp, loamy smell of modern woodlands. The dominant sound would be the constant whisper of wind moving through those tough, tongue-shaped leaves, a dry, rustling counterpoint to the distant calls of the Synapsid giants. The color palette might have been more muted than the vibrant greens of a tropical rainforest. Perhaps duller greens, olive tones, yellows and browns dominated the landscape, reflecting the hardiness of the vegetation. These were forests built for endurance, not for lush extravagance. In the northern hemisphere of Pangaea, the landmass of Laurasia, containing future North America and Eurasia, a different kind of flora held sway. Here, conifers, the ancestors of our modern pines and firs, along with cycads, those palm-like seed plants, were becoming increasingly dominant. These too were hardy trees, well suited to the seasonal variations and potential dryness of the supercontinent's northern reaches. Imagine vast open woodlands of primitive pines, perhaps tougher, more sparsely needled than those we know today, creating a landscape that might feel strangely familiar, yet subtly more ancient, more rugged. These Pangean forests, both the Glossopteris kingdom of the south and the conifer woodlands of the north, were the vital foundation of the entire terrestrial ecosystem. They were the primary producers, capturing the energy of the Permian sun and converting it into the biomass that fed the colossal herds of dicynodonts and parasaurs. They provided shelter, however sparse, for the smaller reptiles and synapsids. They helped to stabilize the soil against the erosive force of the mega monsoons near the coasts. And they continued, albeit perhaps at a slower rate than the carboniferous swamps, to breathe oxygen into the Pangean air. They seemed stable, permanent. They had adapted to the unique challenges of this supercontinent. They stood, silent and green, across vast swathes of Pangaea, unaware that the very ground beneath their roots was about to betray them, unaware that forces building deep within the planet were preparing to unleash a tide of fire and poison that would scorch them from the face of the earth, silencing their rustling leaves and paving the way for the greatest silence life has ever known. The great dying was approaching. The Green Kingdom stood silent, adapted, enduring. The glossopteris forests of the south, the conifer woodlands of the north, they formed the quiet, stable backdrop against which the dramas of the Synapsid age played out. The herds of dicynodonts browsed beneath their branches. The fearsome gorgonopsians stalked through their dappled shade. Life, it seemed, had found its rhythm on this strange, unified continent. The climate was harsh, yes, but predictable in its extremes. The ecosystems, though perhaps simpler than those that came before or after, were functional, established. But the stability was an illusion. The apparent peace was merely the deep breath before the planetary scream. Deep beneath the surface of Pangea, in the region that would one day become Siberia, the Earth itself was stirring. Forces far larger, far more powerful than any living creature, were beginning to converge. The planet's internal heat engine, the same engine that drove the continents together, was preparing to unleash upon the surface world a cataclysm of almost unimaginable scale and duration. The end did not come as a slow decline. It did not come from the sky, like the asteroid that would later claim the dinosaurs. It came from within. It came as an eruption, an event so vast, so prolonged, that it dwarfs any volcanic activity witnessed in human history. This was the trigger for the Great Dying. This was the eruption of the Siberian traps. To understand this event, we must abandon our image of a typical volcano, a single conical mountain spewing ash and lava. The Siberian traps were something else entirely. This was a large igneous province, or LIP. Imagine not a mountain, but a vast region of the Earth's crust, covering thousands upon thousands of square kilometers, that simply tore open. Perhaps triggered by the immense stresses locked within the Pangean supercontinent itself, or perhaps fueled by a plume of superheated rock rising from the deep mantle. The crust fractured. Vast fissures, cracks extending for kilometers, ripped across the landscape of what is now Siberia. And from these gaping wounds, lava began to pour out. This was not the thick, pasty, explosive lava of a Mount St. Helens. This was flood basalt, incredibly hot, incredibly fluid, low viscosity magma that flowed like fiery rivers across the land. It didn't build mountains, it built seas, seas of molten rock that spread outwards relentlessly, burying everything in their path. Picture the scene. A landscape, perhaps initially consisting of low hills, hardy conifer forests, and sluggish braided river valleys. Suddenly the ground splits open. Fountains of incandescent lava erupt along lines stretching for miles, painting the sky orange and black. Rivers of fire, perhaps hundreds of meters deep, flow across the land, consuming forests, boiling rivers, filling valleys. As one layer cools and solidifies into dark, black basalt rock, another eruption begins nearby, pouring fresh lava over the top. Layer upon layer upon layer. And this did not happen over days, or weeks, or even years. The Siberian traps erupted, perhaps intermittently, but relentlessly, for an astonishing duration. Estimates vary, but the main phase of the eruptions may have lasted for up to 1 million years. It was a slow-motion geological catastrophe of almost unimaginable endurance, a wound opening deep within the earth, bleeding fire onto the surface for a millennium of millennia. The scale of this million-year-long eruption is difficult for the human mind to truly grasp. The resulting volcanic rock, the solidified remnants of those ancient lava flows, today covers an area of Siberia larger than Western Europe. Imagine the entire landmass of France, Germany, Spain, and the UK combined, buried beneath layers of dark volcanic stone. In some places, the stack of solidified basalt layers is over 2 kilometers, more than a mile, thick. Think of that. Layer after slow layer of lava, pouring out relentlessly, year after year, century after century, building up a plateau of volcanic rock that reached mountainous heights simply through sheer, flat accumulation. The total volume of lava erupted is estimated to be in the millions of cubic kilometers, perhaps 3, maybe 4 million cubic kilometers of molten rock. That is enough lava to bury the entire continental United States several meters deep. It is enough lava to cover the whole surface of the Moon in a layer nearly 10 meters thick. It was, quite simply, one of the largest outpourings of volcanic material in the last 500 million years of Earth's history. This immense million-year flood of fire was, in itself, a regional apocalypse. Any life that existed in that vast region of Siberia, the hardy conifer forests, the insects, the amphibians clinging to the rivers, perhaps even wandering groups of synapsids, was utterly incinerated, buried beneath an ocean of cooling rock. The landscape itself was transformed into a true hellscape, a vast, elevated volcanic plateau, perpetually shrouded in sulfurous smog, illuminated by the orange glow of countless active fissures. Rivers of incandescent rock flowed across blackened plains. The air itself would have shimmered with heat, thick with the smell of sulfur and burning earth. It was a land utterly inimical to life, a wound on the face of the planet weeping fire. The heat released by this unimaginable volume of molten rock pouring onto the surface for 1 million years would have had a profound direct impact on the regional and perhaps even the global climate, adding another layer of thermal stress to a world already prone to extremes. But the lava itself, for all its terrifying grandeur, for all its local destructive power, the lava was not the weapon that would trigger the greatest mass extinction of all time. The true global devastation, the agent that would poison the atmosphere, choke the oceans, and push the entire biosphere to the very brink of collapse, was not the molten rock flowing across Siberia. It was the invisible consequence of this immense planetary wound. It was the gases. The sheer, inconceivable volume of toxic, climate-altering gases released from this million-year eruption was about to wage chemical warfare on the entire planet. The fire on the land was just the prelude. The true cataclysm was about to unfold in the sky. Magma deep within the Earth is not just molten rock. It is a complex soup, supercharged with dissolved gases, held under immense pressure. Carbon dioxide, water vapor, sulfur compounds, methane, halogens, all are locked within the liquid stone like the fizz trapped inside an unopened bottle of soda. As that magma rises towards the surface, as the pressure decreases, these gases begin to bubble out violently. A volcanic eruption is not just an outpouring of lava, it is a massive degassing event, and the Siberian Traps eruptions were like opening a million-year-long, continent-sized bottle of soda. The sheer volume of gas released into the atmosphere during this extended catastrophe is difficult to fathom, dwarfing the emissions of all human activity throughout history by orders of magnitude. And the type of gas released was a perfect cocktail for planetary disaster. First, and perhaps most insidiously, came the sulfur. Volcanoes are notorious sources of sulfur dioxide, SO2, that sharp, choking gas that gives volcanic fumes their characteristic rotten egg smell. The Siberian Traps were no exception. Immense clouds of SO2, smelling perhaps like rotten eggs on a planetary scale, billowed into the atmosphere from those same gaping fissures, year after relentless year, millennium after millennium. In moderate amounts, sulfur dioxide released high into the atmosphere can actually have a temporary cooling effect, forming tiny sulfate aerosol particles that reflect sunlight back into space. but the sheer, unrelenting volume pouring out of Siberia for hundreds of thousands of years overwhelmed any potential cooling. Instead, it triggered a global chemical catastrophe. High in the Pangean sky, this sulfur dioxide reacted readily with water vapor and oxygen, undergoing a chemical transformation. It became sulfuric acid, H2SO4. Tiny droplets of one of the most corrosive acids known suspended in the clouds, drifting on the global winds. Now, imagine the rain that began to fall upon the late Permian world. It was no longer the gentle, life-sustaining shower that nourished the Glossopteris forests. It was acid rain, and not the mildly acidic rain that causes environmental concern today. The concentration of sulfuric acid in the Permian atmosphere may have been so high that the rain falling across the globe was potentially as acidic as lemon juice or even vinegar. Picture this corrosive rain falling relentlessly, season after season, year after year, across the entire supercontinent of Pangea. The effects on the terrestrial ecosystem, already perhaps stressed by the subtle beginnings of climate change from the eruption's heat, would have been swift and utterly devastating. The forests, those hardy Glossopteris woodlands of the south, the conifer forests of the north, they were now being chemically burned from above. The acid rain would have stripped the protective waxes from leaves, leaving them vulnerable to disease and desiccation. It would have directly damaged the delicate photosynthetic machinery within the plant cells, hindering their ability to grow, to breathe, to live. Over time, vast swathes of the Permian forests would have simply withered, sickened, and died. Their leaves burned brown, their branches left bare and skeletal under a sky that offered no relief, only poison. Imagine entire landscapes transformed into ghostly, grey woodlands, silent and dead. The very air, once cleansed by these green lungs, was now turning against them, delivering a slow, burning death from above. The sky itself had begun to weep poison. But the acid rain, devastating as it was only one prong of the chemical assault unleashed by the Siberian traps. Alongside the sulfur dioxide came another, even more abundant and ultimately more consequential, gas: carbon dioxide, CO2. Magma is naturally rich in dissolved CO2, and the sheer volume of magma erupted over that million-year span meant that billions upon billions, perhaps trillions, of tons of this potent greenhouse gas were injected directly into the atmosphere. CO2 is the planet's primary thermostat. It acts like an invisible blanket, trapping heat radiating from the Earth's surface and keeping the world warm enough for liquid water and life to exist. For millions of years, the Pangean world had maintained a relatively stable, albeit warm, climate with the carbon cycle, the slow exchange of carbon between rocks, oceans, atmosphere, and life, keeping the thickness of this blanket roughly constant. But the Siberian traps were not a gentle nudge to the thermostat. They were like throwing gasoline onto a fire, or more accurately, like piling dozens of thick, heavy blankets onto a planet that was already comfortably warm. The atmospheric concentration of CO2 began to skyrocket, perhaps reaching levels thousands of parts per million, levels not seen for hundreds of millions of years, and far exceeding anything predicted in even the most extreme scenarios of our own future climate change. And CO2 was likely not the only greenhouse gas amplifying the effect. The eruptions also released vast quantities of methane, CH4. Methane is an even more potent greenhouse gas than CO2, trapping heat with brutal efficiency, although it persists for a shorter time in the atmosphere. Where did this methane come from? Some likely originated from the magma itself. But tragically, the Siberian traps erupted through one of the largest deposits of coal and organic-rich rock on the planet, the remnants of those vast carboniferous swamps. The intense heat of the rising magma essentially cooked these ancient coal seams, releasing vast stores of methane directly into the air. It was like adding rocket fuel to the already raging greenhouse fire. The effect was not subtle, nor gradual. The planet's delicate thermostat was broken, jammed permanently in the on position. Earth began to plunge into a runaway greenhouse effect. Global average temperatures began to soar. Geological evidence, chemical signatures locked within ancient rocks, suggests a rapid and terrifying increase, perhaps by as much as 10 degrees Celsius or even more in a relatively short geological time frame. 10 degrees. To put that in perspective, the warming that scientists predict for our own future, which carries potentially catastrophic consequences, is measured in just a few degrees. This was an order of magnitude larger. It was a planetary fever breaking out on a geological timescale. The warming was not uniform. The equatorial regions, already warm, likely became lethally hot, perhaps reaching average temperatures that were simply unsurvivable for most complex life. Land surface temperatures in the tropics might have regularly exceeded 40 degrees Celsius, 104 Fahrenheit, perhaps even reaching scorching peaks of 50 or 60 degrees Celsius, 120 to 140 Fahrenheit. Imagine vast swathes of the Pangean heartland, already prone to dryness, simply baking into sterile, cracked earth under a relentless, greenhouse-intensified sun. Even the oceans, with their immense thermal mass, could not escape the heat. Sea surface temperatures rose dramatically, especially in the Tethys Sea, perhaps reaching levels that would be lethal to most marine life today. This warming, as we shall see, would have devastating consequences beyond just the heat itself, fundamentally altering ocean chemistry and oxygen levels. This intense global heatwave was a silent, invisible killer. The air itself, thick with heat-trapping gases, became a suffocating blanket. Life on land, particularly the large, active synapsids like the gorgonopsians and dicynodonts, with their potentially high metabolisms, would have struggled immensely. Imagine those powerful predators unable to effectively cool their bodies in the relentless heat, their stamina failing, their hunting grounds turning into barren, sun-scorched plains. Imagine the herds of tusked herbivores searching desperately for dwindling water sources under a sky that offered no relief, only ever-increasing heat. The runaway greenhouse effect, driven by the relentless volcanic outgassing, was the second great blow delivered by the Siberian traps. It compounded the damage of the acid rain. It turned the familiar world into an oven. It stressed ecosystems, already weakened, towards their breaking point. And it set the stage for the next phase of the catastrophe, a crisis that would attack not just the land, but the very lifeblood of the planet, the oceans themselves. The poison falling from the sky, the relentless acid rain, did not remain confined to the land. Every drop that burned the leaves of the Glossopteris forests, every acidic streamlet that carved its way through the dying soil, inevitably flowed downhill. Rivers, once perhaps carrying clear water from Pangea's interior mountains, now ran thick and brown, choked with sediment stripped from the collapsing landscapes. And they carried something else, their burden of acidity and the toxic metals leached from the poisoned earth. All of this flowed inexorably towards the sea, towards the vast Panthalassa and towards the warm, sheltered Tethys. The oceans, which might have seemed like a distant, stable refuge from the chaos unfolding on land, were about to receive the full, concentrated fury of the atmospheric poison. The first impact was chemical. Ocean acidification. The oceans act as a vast natural sponge, absorbing enormous quantities of carbon dioxide from the atmosphere. Normally, this process is slow, balanced, part of the Earth's long-term carbon cycle, buffered by the ocean's own complex chemistry. but the sheer overwhelming volume of CO2 released by the Siberian traps, pouring into the sky for 1 million years, saturated this natural system. As CO2 dissolves in seawater, it reacts with water molecules to form carbonic acid, H2CO3. This is a weak acid, the same substance that gives fizzy drinks their slight tang. But when introduced into the ocean on a planetary scale relentlessly for millennia, even a weak acid can have profound consequences. It begins to lower the ocean's pH, making the water more acidic, more corrosive. This process strikes directly at the heart of marine ecosystems by attacking the ability of organisms to build shells and skeletons. Many marine creatures, from microscopic plankton at the base of the food web to the massive reefs built by sponges and algae, construct their hard parts out of calcium carbonate, the mineral building blocks of limestone and chalk. They extract dissolved calcium ions and carbonate ions from the seawater and combine them to create their protective homes. But carbonic acid disrupts this delicate chemistry. The excess hydrogen ions released by the acid react with the available carbonate ions in the water, essentially stealing them away. This makes it much harder for shell-building organisms to find the raw materials they need. Imagine trying to build a house when bricks are suddenly becoming scarce. And as the acidity increases further, the water itself can become corrosive to existing calcium carbonate structures. Shells and skeletons don't just become harder to build, they can actually begin to dissolve. Imagine the effect on the vibrant, shell-rich ecosystems of the late Permian. The microscopic plankton, the tiny single-celled organisms that formed the very base of the marine food web, would have been among the first and hardest hit. Their delicate calcium carbonate shells became difficult to form, perhaps thinner, weaker, or malformed. Populations would have crashed, sending shockwaves up the entire food chain. The great reefs of the Tethys Sea, built by calcareous sponges, bryozoans and algae, were facing a double assault. The warming waters were likely already causing stress, perhaps bleaching. Now the acidifying water was making it harder for them to grow, perhaps even beginning to dissolve their existing stony structures. The intricate cities of the Permian seas began to crumble, and the brachiopods, those incredibly abundant filter-feeding shelled creatures that carpeted vast areas of the seafloor, their entire way of life depended on their ability to build and maintain their calcium carbonate shells. In the increasingly acidic water, this became an energetically costly, perhaps impossible task. We see evidence of this in the fossil record. Brachiopod shells from the extinction interval sometimes appear thinner, stunted, deformed. They were struggling, dissolving in place. Even the ammonites, those successful coiled-shelled cephalopods, were vulnerable. Building and maintaining their complex, chambered shells in corrosive waters would have become a major metabolic burden. Ocean acidification was a silent, invisible crisis unfolding molecule by molecule in the water itself. It didn't suffocate creatures directly, but it attacked their armor, their homes, their very ability to exist in a physical form. It undermined the structural integrity of entire ecosystems, from the microscopic base to the largest reefs. The oceans were becoming chemically hostile, and this chemical assault was compounded by another, even more insidious consequence of the planetary fever. The ocean was losing its breath. The chemical assault of acidification was undermining the very structure of marine life, making it harder for creatures to build their shells, their skeletons, their homes. But the Siberian traps had unleashed another equally devastating blow upon the oceans, one aimed not at their substance, but at their breath. The oceans were beginning to suffocate. This crisis was driven primarily by the relentless heat pouring into the global system from the runaway greenhouse effect. We must remember a simple, fundamental law of physics. Warm water holds significantly less dissolved gas than cold water. Think of a glass of cold soda fizzing with dissolved carbon dioxide. As it warms up, the gas escapes and the drink goes flat. The same principle applies with devastating consequences to oxygen in the ocean. As the global seas heated up, the surface waters perhaps reaching lethal temperatures in the tropics, and even the deeper waters slowly warming, their intrinsic ability to hold on to dissolved oxygen plummeted. The water itself was becoming less capable of sustaining the breath of life. But the warming caused another, even more insidious problem. It stratified the ocean. Normally, the oceans are in constant, slow motion. Cold, dense, oxygen-rich water sinks near the poles and creeps slowly through the abyssal depths, bringing vital oxygen to the deep sea. Warmer surface waters mix with cooler layers below through wind and currents. This global circulation acts like the planet's aquatic respiratory system, ventilating the vast volume of the ocean. But as the surface waters became significantly warmer and therefore less dense than the waters below, a strong boundary layer formed, a thermocline. This acted like an invisible lid, preventing the warm, potentially oxygenated surface waters from mixing downwards. The ocean's natural ventilation system began to fail. The deep sea was being cut off from its oxygen supply. At the same time, the chaos unfolding on land and in the shallow seas was sending a deadly rain down into the depths, as plankton blooms, perhaps initially fueled by nutrients washing off the dying land, crashed and died, as the collapsing coastal ecosystems released vast amounts of dead organic matter. All of this biological debris slowly sank into the deep ocean, and in the darkness, bacteria went to work, decomposing this falling rain of death. This process, decomposition, consumes oxygen relentlessly. In the already oxygen-starved deep waters, cut off from resupply from above, this bacterial activity stripped away what little oxygen remained. The result was the terrifying, inexorable spread of ocean anoxia. Vast swathes of the ocean becoming depleted or entirely devoid of dissolved oxygen. Imagine the deep sea floor first. Already naturally lower in oxygen, it was now completely cut off. The slow-moving creatures that lived there, the trilobites, the deep-water brachiopods, the strange worms and burrowers adapted to the abyssal plains, faced utter asphyxiation. The seafloor, once perhaps teeming with a slow, hidden life, became a graveyard. Anything that could not tolerate near-zero oxygen levels simply died. Microbial mats perhaps endured or even thrived in these conditions, but the complex animal life vanished. And this anoxia didn't just stay in the deepest abyss. The oxygen minimum zones, those layers of breathless water, began to expand upwards, creeping, layer by suffocating layer, from the abyssal plains towards the sunlit surface. In some regions, particularly in enclosed basins or areas with sluggish circulation, like perhaps parts of the warm Tethys Sea, these oxygen-starved waters may have reached all the way up into the shallows, turning even the coastal zones, the supposed refuges, into breathless death traps. The ocean, the cradle of life, the vast, stable reservoir that had nurtured evolution for billions of years, was beginning to suffocate from the inside out. The heat was rising, the water was turning corrosive, and now the very breath was being stolen from its depths. This asphyxiation was a silent, invisible killer, creeping through the water column, adding another layer of profound, inescapable stress to marine ecosystems already reeling from the heat and the acid. Life in the Permian seas was being attacked from all sides. The greatest dying in the history of the ocean was now truly underway. The Permian oceans were now caught in a terrifying three-pronged assault. The relentless heat pouring in from the runaway greenhouse sky was raising temperatures to lethal levels, especially near the surface. The corrosive effect of dissolved carbon dioxide was acidifying the water, making it difficult, perhaps impossible for shelled creatures to build or maintain their homes. And now, the suffocating grip of anoxia, spreading upwards from the deep, was stealing the very breath from the water column. Heat, acid, lack of air. It was a simultaneous, systemic failure of the marine environment, and the consequences for the life that had flourished there for tens of millions of years were catastrophic. Consider the great reef systems that had thrived in the warm, shallow waters of the Tethys Sea. These intricate cities, built patiently by calcareous sponges, bryozoans, and algae, were exquisitely sensitive to environmental change. The rising temperatures likely caused bleaching, stressing the symbiotic relationships within the reef community. The increasing acidity directly attacked their calcium carbonate skeletons, hindering growth and perhaps even causing existing structures to dissolve. And now the encroaching anoxia, perhaps washing over the reefs in periodic upwellings of oxygen-poor water from below, would have delivered the final suffocating blow. The fossil record tells a stark story. These vibrant, complex Permian reefs simply vanished. Worldwide, reef-building activity shut down almost completely. The intricate architecture collapsed, leaving behind only crumbling skeletons, perhaps quickly overgrown by microbial mats in the poisoned waters. It would take millions of years, well into the subsequent Triassic period, for entirely new groups of organisms, primarily the ancestors of modern corals, to slowly, painstakingly reinvent the art of reef building from scratch. The great cities of the Permian seas fell silent. And what of the creatures that carpeted the sea floor? The brachiopods, those overwhelmingly abundant filter feeders whose shells had paved the shallow oceans for much of the Paleozoic. They were direct victims of the hostile chemistry. Their calcium carbonate shells were dissolving. Their ability to filter food from the water was likely impaired by the stress of heat and low oxygen. While a few hardy lineages would cling to existence in refuges, the vast majority perished. Their long, dominant reign over the seafloor was shattered. They would never again achieve the ecological prominence they held before the Great Dying. The ammonites, those coiled-shelled cephalopods that had successfully navigated previous environmental crises, they too suffered immensely. Their complex shells were vulnerable to acidification. Their active swimming lifestyle required abundant oxygen, which was rapidly disappearing from large parts of the water column. And perhaps crucially, their tiny planktonic larvae would have been acutely vulnerable to both the corrosive water and the extreme heat. Like the brachiopods, a few resilient ammonite lineages famously survived, but their diversity was decimated. The vast majority of Permian ammonite families vanished forever. Even the trilobites, those ancient iconic arthropods that had survived for over 250 million years, weathering previous mass extinctions, their time had finally run out. Already perhaps in decline, the combination of stresses in the late Permian, the warming waters, the spreading anoxia on the seafloor where many lived, proved too much. The last trilobites disappeared from the fossil record, marking the final end of one of the longest and most successful runs in the history of animal life. The story repeats itself across almost every group of marine organisms. Fish, plankton, echinoderms like the sea lilies, all experienced devastating losses. This was the marine chapter of the Great Dying, and its scale is almost incomprehensible. Paleontologists, painstakingly counting the fossil lineages that disappear across that dark boundary line in the rock record, estimate that somewhere between 80 and 96% of all marine species vanished forever. Think about that. Perhaps as few as 1 in 20 creatures living in the oceans survived. Entire ecosystems were erased. Ancient dynasties were extinguished. The oceans, which had seemed so vast, so stable, so resilient, were effectively emptied. The intricate web of life, built patiently over hundreds of millions of years, was torn apart. The silence that was falling upon the scorched and burning land now echoed profoundly and chillingly beneath the waves. The earth, both land and sea, was entering its darkest hour. The devastation unfolding beneath the waves, the suffocating, acidifying, emptying oceans, was mirrored, perhaps even surpassed, by the catastrophe sweeping across the single great landmass of Pangaea. The poisons released into the sky by the Siberian traps attacked the terrestrial world with a brutal, multi-pronged efficiency, turning the familiar landscapes into a true planetary hellscape. We saw earlier how the relentless acid rain began to burn the forests, chemically scorching the leaves and poisoning the soil. We felt the initial rise in temperature as the first waves of carbon dioxide began to build. But now, as the eruptions continued century after century, as the greenhouse gases accumulated to truly staggering levels, the full, terrifying force of the runaway climate change was unleashed upon the land. The heat became unbearable. The Pangean interior, already prone to extreme temperatures, transformed into a furnace far exceeding anything the planet had experienced in hundreds of millions of years. Imagine those vast central deserts, the searing rock, the endless dunes, now baking under a sun amplified by an atmosphere thick with heat-trapping gases. Surface temperatures likely soared to levels simply incompatible with complex life. Water, already scarce, vanished completely from vast regions. The land cracked, warped, and radiated a heat that could be felt even miles away. Even the coastal regions, once perhaps refuges of relative moisture, succumbed. The mega monsoons, while perhaps initially intensifying due to the chaotic climate, eventually likely faltered or shifted unpredictably. The relentless heat evaporated moisture faster than the rains could replenish it. The hardy, glossopteris forests of the south, already weakened by the acid rain, now faced lethal drought and heat stress. The conifer woodlands of the north withered under the same assault. Wildfires, perhaps ignited by lightning strikes in the tinder-dry, dying vegetation, though the exact oxygen levels during the peak crisis are unknown, debated, affecting flammability, may have raged across the continents, consuming the remaining biomass in great choking pyres. Imagine the scene: skeletal forests standing silent under a hazy orange sky, the air thick not just with volcanic smog, but with the smoke of a burning world. The soil itself, the very foundation of terrestrial life, was dying, stripped bare by the death of the forests, poisoned by acid rain, and baked by the intense heat. It lost its structure, its fertility. Essential nutrients were washed away by erratic floods, while toxic metals accumulated. Then, the relentless Pangean wind began its work, picking up the dry, loose soil particles, creating immense dust storms that might have dwarfed anything seen in human history. These storms would have further scoured the land, stripping away any remaining pockets of life-giving earth and potentially carrying toxic dust across vast distances, spreading the devastation. The land was bleeding its very skin into the sea and sky, and the air itself became another enemy. As the great forests collapsed, the planet's green lungs were failing. The production of oxygen through photosynthesis plummeted. At the same time, the decomposition of the vast amounts of dead and dying vegetation consumed oxygen relentlessly, and the warming oceans, less able to hold dissolved gases, likely released some of their stored oxygen, further destabilizing the atmospheric balance. The result was a significant drop in atmospheric oxygen levels. Estimates vary, but oxygen concentrations may have plummeted to perhaps 15% or even lower, levels found today only at extremely high altitudes. For the large, active synapsid creatures still clinging to existence, this would have been a slow, agonizing suffocation. The air became thin, unsatisfying. Each breath delivered less fuel. Imagine the great Gorgonopsians, those powerful hunters now lethargic, gasping, unable to sustain the chase. Imagine the herds of Dicynodonts, weakened by starvation and heat, now struggling simply to draw enough breath to stand. Size and power, once assets, became fatal liabilities in a world where every breath was a struggle. Heat, acid, drought, fire, poisoned soil, thin air. The terrestrial world was collapsing from within, attacked on every front. The complex ecosystems built over millions of years were unraveling. The plants were dying, the soil was eroding, the air was becoming unbreathable. For the creatures that had ruled Pangea, the end was not a swift, dramatic event. It was a slow, grinding attrition. It was starvation, heat stroke, dehydration, suffocation. The land was falling silent. And so, the crescendo of catastrophe reached its peak. The million-year-long volcanic pulse from Siberia had injected its full measure of poison into the global system. The planet, pushed far beyond its limits, responded with a spasm of death unlike any other in its long, violent history. Heat, acid, drought, fire, poisoned soil, thin air on land. Heat, acid, suffocation beneath the waves. These were not separate events hitting isolated ecosystems. They were a simultaneous, interconnected global assault on the very fabric of the biosphere. The web of life, woven patiently over 3 billion years, was being torn apart, thread by thread, until almost nothing remained. This was the culmination. This was the Permian-Triassic extinction event, known to science simply and starkly as the Great Dying. It stands alone in the grim annals of Earth's history as the largest mass extinction event ever recorded. Nothing else. Not the Ordovician Ice Age, not the Devonian Oceanic crises, not even the asteroid impact that famously claimed the dinosaurs, comes close to its scale of devastation. It was a moment when the thread of complex life, spun so patiently through the Paleozoic era, nearly snapped completely. The statistics, pieced together painstakingly by paleontologists counting the fossil lineages that vanish across that dark boundary line in the rock record, are stark, almost numbing in their totality. In the oceans, as we saw, the losses were almost absolute. Somewhere between 80 and 96% of all marine species vanished forever. Think of that. Perhaps as few as 1 in 20 creatures living in the sea survived. Entire ecosystems, like those vibrant Permian reefs, were simply erased. Ancient and dominant groups, like the trilobites, which had persisted for nearly 300 million years, were finally completely extinguished. The brachiopods, the crinoids, the ammonites, all were decimated, reduced to a handful of scattered, traumatized survivors. The oceans fell into a profound, echoing silence. On land, the picture was scarcely better. Estimates suggest around 70%, perhaps more, of terrestrial vertebrate species disappeared. The great Synapsid dynasties that had ruled Pangea were shattered. The terrifying Gorgonopsians, the apex predators, vanished completely, leaving no descendants. The vast herds of Dicynodonts, the ecological foundation of the terrestrial world, were almost entirely wiped out, save for 1 or 2 incredibly resilient lineages. The armored pariasaurs were gone. Many lineages of early reptiles and amphibians also vanished. The world was emptied of its large animals. And the devastation likely extended deep into the unseen world as well. Evidence suggests this was also the largest known mass extinction of insects, the normally resilient masters of survival, succumbing to the poisoned air and collapsing plant life. Even the plants themselves, the primary producers, suffered catastrophic losses, with entire forest types, like the great Glossopteris kingdom, disappearing globally. This was not a selective pruning of the tree of life. This was a near-total clear-cutting. It was indiscriminate, brutal, and global. Life everywhere, in every environment, at almost every trophic level, was impacted. Imagine the planet in the immediate aftermath, perhaps as the Siberian volcanoes finally began to quiet their million-year fury. The land is a scarred, eroded wasteland, baking under a still oppressive greenhouse sun, perhaps shrouded in a perpetual haze of dust and volcanic smog. The great forests are gone, replaced by skeletal remains, or perhaps hardy, opportunistic ferns clinging to life in sheltered gullies. The rivers run thick and brown, carrying the dead skin of the continents out to the empty, silent sea. The air is thin, hot, and difficult to breathe, and the overwhelming impression is one of profound, almost deafening silence. The complex chorus of the Permian world, the calls of amphibians, the rustle of diverse forests, the bellowing of dicynodont herds, the unseen movements of countless smaller creatures, has fallen quiet. What remains is the sound of the planet itself. The wind whistling over barren rock, the hiss of acid rain perhaps still falling intermittently, the slow trickle of poisoned water finding its way to the sea. The great firestorm had passed. The Siberian volcanoes fell silent. The runaway greenhouse eventually began to subside as the planet's slow geological cycles painstakingly started the immense task of reabsorbing the excess carbon from the sky. The acid rain ceased. But the world left behind was not one of immediate recovery. It was a world suffering from a profound planetary-scale trauma, a world emptied, simplified, and profoundly silent. Yet, even in the deepest, darkest night, a few sparks inevitably remain. Life, reduced to a flicker, somehow endured. Amidst the near-total devastation on land, where perhaps 70% or more of vertebrate species had vanished, a few hardy survivors emerged from the wreckage. They were not the strong, the specialized, or the dominant players of the old world. They were the adaptable, the generalists, perhaps simply the lucky. And among these survivors, one creature stands out, not just for enduring the apocalypse, but for positively thriving in its immediate aftermath. Its fossil remains become overwhelmingly, almost comically, abundant in the rock layers immediately following the Great Dying, a testament to its incredible resilience in the face of planetary catastrophe. This was the unlikely inheritor of the broken world, Lystrosaurus. Let us try to picture this creature, this ultimate survivor. It was a Synapsid, a member of that once great dynasty that had ruled the Permian. Specifically, it was a dicynodont, belonging to that group of tusked, beaked herbivores that had previously roamed Pangea in vast herds of diverse species. But Lystrosaurus was not a giant. It was perhaps pig-sized or sheep-sized, maybe reaching about 1 meter or 3 feet in length. Its body was stout, barrel-shaped, typically dicynodont in its build, with sturdy, albeit short, limbs. Its face was peculiar, a short, flattened snout ending in that characteristic turtle-like beak, perfect perhaps for cropping tough, low-growing vegetation. 2 prominent tusks, usually larger in males, jutted downwards from its upper jaw. Their exact function, whether for defense, display, or digging, still debated. Its nostrils were positioned unusually high up on its snout, almost near its eyes, giving it a slightly comical, almost pug-like appearance. In the diverse, competitive world before the extinction, Lystrosaurus was just one player among many, a relatively unremarkable medium-sized herbivore, perhaps widespread, but certainly not dominant. But it possessed a unique combination of traits, a biological toolkit that, purely by chance, turned out to be the perfect survival kit for the end of the world. What was its secret? Why did Lystrosaurus endure while the mighty Gorgonopsians and most of its larger dicynodont cousins vanished? Scientists believe several factors contributed to its astonishing success. First, its diet. As a dicynodont, It was likely a generalist herbivore, capable of feeding on a wide variety of tough, low-lying vegetation, perhaps roots, tubers, stems, the hardier disaster flora, like ferns and lycopods that might have clung to existence even as the great Glossopteris forests died. Its powerful beak could crop, and perhaps its tusks helped it dig, accessing underground food sources unavailable to more specialized browsers. In a world of collapsing food webs, being an unfussy eater was a huge advantage. Second, its potential lifestyle. Fossil evidence, including analysis of its sturdy limb bones and shoulder structure, suggests Lystrosaurus may have been a powerful burrower. By retreating underground, it could have escaped the worst of the searing surface heat, the acid rain, and perhaps even found refuge from the thinned, oxygen-poor air in the more stable microclimate of a burrow. An underground lifestyle offers powerful protection from environmental extremes, a crucial advantage during a global catastrophe. Third, its physiology. Those high-placed nostrils have led some to speculate that Lystrosaurus might have been semi-aquatic, or at least comfortable spending time in or near water, perhaps feeding on aquatic vegetation, another potential refuge. Furthermore, some studies suggest that dicynodonts, as synapsids, might have possessed a more efficient respiratory system than true reptiles, perhaps involving a diaphragm, allowing them to cope slightly better with the low oxygen levels. Their potentially slower, perhaps more cold-blooded-like metabolism compared to the active Gorgonopsians might also have been an advantage, requiring less food and oxygen simply to survive. Finally, its geographic distribution. Even before the extinction, Lystrosaurus seems to have been incredibly widespread, found across the vast expanse of Pangea, from Antarctica to Russia to India. This huge range meant that at least some populations, somewhere, were likely to survive the localized impacts of the catastrophe, providing a reservoir from which the species could later repopulate the empty world. Whatever the precise combination of reasons, Lystrosaurus didn't just survive, it dominated. In the earliest Triassic rock layers, immediately following the extinction boundary, its fossils account for as much as 90, even 95% of all terrestrial vertebrate fossils found. For a brief, strange period in Earth's history, it was almost the only large animal left on land. Imagine those early Triassic landscapes, barren, recovering, perhaps dotted with hardy disaster-adapted ferns and club mosses. And wandering across this empty stage in vast, unchallenged numbers are herds upon herds of Lystrosaurus. It is a world remade, temporarily, in the image of this single, unlikely survivor. A stark, almost eerie testament to the unpredictable nature of extinction, where the meek, the generalist, and perhaps the lucky can inherit the earth when the mighty fall. But its reign was a symptom, not a cure. The planet was still deeply wounded. The overwhelming abundance of Lystrosaurus in the earliest Triassic rocks is not a sign of a healthy, thriving ecosystem. It is the opposite. It is a symptom of profound ecological collapse. It is the signature of an empty world. The Great Dying had acted like a planetary wildfire, sweeping across Pangaea and scouring the terrestrial ecosystems bare. What remained in the immediate aftermath was a landscape depopulated, simplified, and profoundly silent. Imagine the contrast. Just a few million years earlier, the Permian world, while harsh, had teemed with a strange and diverse fauna. Great herds of various dicynodont species, alongside the armored pariasaurs, browsed the Glossopteris woodlands. Fearsome Gorgonopsians stalked their prey. Smaller synapsids, early reptiles, amphibians, and a world of insects filled countless niches in the undergrowth, along the riverbanks, and in the trees. It was a complex, multi-layered ecosystem, the product of tens of millions of years of evolution on the supercontinent. Now, in the wake of the catastrophe, that complexity was gone. The fossil record reveals a staggering loss, 7 out of every 10 land vertebrate species had vanished. Entire families, entire orders, entire ancient dynasties that had ruled for millennia were simply gone. The great predators were extinct. The apex hunters, like the Gorgonopsians, left no descendants. For a time, the ecological role of the large carnivore simply ceased to exist on Pangaea. This absence of predation is likely one of the key factors that allowed the surviving Lystrosaurus populations to explode, reproducing and spreading virtually unchecked across the empty landscape. Most of the large herbivores were also gone. The diverse dicynodont groups were decimated, with only Lystrosaurus and perhaps a few very close rare relatives surviving. The armored pariasaurs vanished completely. The complex plant-eater guilds that had structured the Permian ecosystems were reduced to almost a single, dominant player. Even the smaller creatures suffered immense losses. Many lineages of insects, amphibians, and smaller reptiles were extinguished. The world was not just emptier of giants, it was emptier at almost every level. The very structure of the ecosystem had collapsed. The intricate food webs, the complex relationships between predator and prey, herbivore and plant, scavenger and carcass, these had been torn apart. What remained was a simplified, almost skeletal ecosystem, dominated by a few hardy, generalist survivors. It was like comparing a vibrant, bustling city to a ghost town, with only a handful of resilient inhabitants remaining, wandering through the deserted streets. And this emptiness was compounded by the sheer hostility of the environment itself. The land was not just empty, it was wounded. The soil, stripped of its protective plant cover and poisoned by acid rain, was impoverished, unstable, and perhaps toxic. The vegetation that slowly began to reclaim the land consisted primarily of hardy, fast-growing disaster taxa, ecological opportunists like certain types of ferns, such as dicroidium, and lycopods, club mosses, that could tolerate the harsh conditions. But these formed low-diversity ecosystems, offering poor nutrition compared to the forests they replaced. Freshwater sources, rivers and lakes, were likely still choked with sediment washed from the eroded land, potentially acidic, and perhaps prone to toxic algal blooms fueled by the unbalanced nutrient runoff. The climate remained unstable, perhaps swinging between intense heat spells inherited from the greenhouse pulse and harsh dryness. Survival, even for the survivors, was likely a constant struggle. Life existed in a state of low energy, low diversity, and profound stress. The silence that had fallen upon the land was not the peaceful quiet of a healthy ecosystem at rest. It was the silence of absence, the silence of death. This empty world syndrome, this prolonged period of low biodiversity and ecological simplicity following a mass extinction, is a stark reminder of how difficult it is to rebuild a complex ecosystem once it has collapsed. Recovery is not automatic. It is a slow, difficult, and contingent process. It requires not just the survival of individual species, but the painstaking reweaving of the intricate connections between them. The reign of Lystrosaurus, this strange period when one unremarkable herbivore seemed to inherit the earth, lasted for perhaps a few million years. But it was a temporary kingdom, a placeholder in a world waiting to heal. The true recovery, the rise of the next great dynasties that would define the Mesozoic era, required time. It required the slow stabilization of the climate, the gradual detoxification of the environment, and the patient work of evolution, exploring new possibilities within the handful of lineages that had made it through the fire. The stage was empty, waiting for the next act to begin. While Lystrosaurus wandered the empty landscapes in its unchallenged millions, a silent ecological placeholder, the true seeds of the future were stirring elsewhere. The Synapsid dynasty, though not entirely extinguished, Lystrosaurus itself was proof of that, and other, smaller lineages also clung on, had lost its grip on the world. Its great predators were gone, its diverse herbivore guilds were shattered, the throne of planetary dominance lay vacant, and into this void, another group of survivors began to cautiously, then decisively, step forward. These were the creatures that had lived in the shadows during the Permian, the understudies patiently waiting for their chance. These were the sauropsids, the reptile line archosaurs. Specifically, it was a subgroup within the sauropsids known as the archosauromorphs, the ruling lizard forms, that seized the opportunity presented by the empty Triassic world. This diverse group had scraped through the Great Dying, represented perhaps only by small, adaptable, lizard-like forms. But they possessed a unique combination of resilience and evolutionary potential that made them perfectly suited to inherit the wounded planet. What set them apart? Archosaurs possessed efficient respiratory systems, perhaps better adapted than many synapsids to the lower oxygen levels that likely persisted in the early Triassic aftermath. They were masters of water conservation, crucial in the potentially drier Pangean climate, and they carried within their genes the potential for remarkable evolutionary innovation, particularly in their posture and locomotion. As the Triassic period dawned and the immediate shock of the extinction began to subside, these archosaur survivors began to diversify, radiating out into the countless empty ecological niches left vacant by the fallen synapsids. It was not an overnight conquest. The recovery was slow, measured in millions of years, but the direction was clear. The future belonged to them. Two main branches emerged from this initial archosaur radiation, embarking on different, yet equally successful, evolutionary paths. One branch led towards the lineage we know today as the Crurotarsi, or Pseudosuchia, the crocodile line archosaurs. In the early Triassic, these were not the slow, semi-aquatic ambush predators we picture today. Many were fast, agile, terrestrial hunters. Creatures like Erythrosarcus, a large-headed predator perhaps 5 meters long, became some of the first new apex carnivores to evolve in the post-extinction world, likely preying upon the abundant Lystrosaurus and other smaller survivors. Other crocodile line archosaurs experimented with armor, like the heavily plated etosaurs, becoming well-defended herbivores. Still others, like the Rauisuchians, evolved into fearsome quadrupedal predators, resembling crocodiles on long upright legs, briefly challenging the dinosaurs for dominance later in the Triassic. This branch was incredibly diverse and successful throughout the Triassic period, filling many of the roles once held by the vanished synapsids. But it was the other main branch of archosaurs that held the key to the truly revolutionary future. This was the Avametatarsalia, the bird metatarsal line. This lineage included the pterosaurs, which would eventually conquer the skies. But most significantly, it included the Dinosauromorpha, the group that contained the direct ancestors of the dinosaurs. In the early and middle Triassic, these dinosauromorphs were still relatively small and perhaps uncommon. Creatures like Lagerpeton or Marsuchus were lightly built, perhaps only a meter long, and crucially, many showed clear adaptations for bipedal locomotion, running efficiently on 2 legs. Their hips were evolving, their leg bones lengthening, their ankles becoming more specialized for agile movement. Imagine these small, swift creatures darting across the recovering Triassic landscape, perhaps hunting insects or small vertebrates. Their quick movements a stark contrast to the lumbering gait of Lystrosaurus. They were not yet dominant. They were likely overshadowed by their larger crocodile line cousins, but they possessed a blueprint for success, efficient locomotion, potentially higher metabolisms, and an inherent adaptability. As the Triassic progressed, as the climate slowly stabilized, as ecosystems began to regain some complexity, these small bipedal dinosauromorphs continued to evolve. Their posture became more upright. Their breathing became more efficient, perhaps developing the one-way airflow system still seen in birds today. And then, sometime around the Middle Triassic, perhaps 230 million years ago, the first true dinosaurs appeared. Creatures like Eoraptor or Herrerasaurus, still relatively small by later standards, but possessing all the key features that would define their dynasty. An upright stance with legs held directly beneath the body, specialized hip and ankle structures allowing for efficient movement, and likely a higher metabolic rate than their contemporaries. The age of dinosaurs had not yet truly begun. They were still just one group among many, competing in a world still recovering from catastrophe. But the seeds had been sown. The archosaurs, rising from the ashes of the Great Dying, had diversified, experimented, and finally produced the lineage that would inherit Pangea and rule the planet for the next 160 million years. The silence was breaking, replaced by the quick footsteps of a new kind of ruler. While the archosaurs, particularly the ancestors of dinosaurs, were making their bold evolutionary moves out in the open, seizing the vacant niches of the recovering Triassic world, another, quieter drama was unfolding in the shadows. Another group of survivors from the Great Dying was pursuing a different strategy, not one of immediate dominance, but of stealth, adaptation, and patient endurance. These too were synapsids, remnants of that once great dynasty that had ruled the Permian. But they were not the lumbering Lystrosaurus. They belonged to a different, more advanced subgroup, the cynodonts, the dog-teeth. These creatures represented the cutting edge of synapsid evolution before the catastrophe. They had already developed many traits we associate with mammals: increasingly differentiated teeth, evidence of a secondary palate separating the mouth from the nasal passage, allowing them to breathe while chewing, crucial for an active metabolism, and perhaps even whiskers and fur, hinting at developing warm-bloodedness. But the Great Dying hit them hard. While some lineages survived, they did not explode onto the scene like the archosaurs. Instead, they seem to have adopted a different path, one perhaps dictated by the new ecological reality, a world increasingly dominated by their fast-evolving reptilian cousins. The cynodonts of the early and middle Triassic remained relatively small. Creatures like Thrinaxodon, found in the same early Triassic rocks as Lystrosaurus, were perhaps the size of a cat or a small dog. Cynognathus, appearing slightly later, was larger, perhaps wolf-sized, and a formidable predator in its own right, but still overshadowed by the largest crocodile-line archosaurs emerging at the same time. Imagine these creatures now, living alongside the early dinosaurs and the diverse crocodile-line rulers. They are perhaps less visible. Their lives lived closer to the ground, perhaps under the cover of darkness. Picture Thrinaxodon, a small, possibly burrowing cynodont. Fossil evidence, including skeletons found curled up within fossilized burrows, strongly suggests this lifestyle. By retreating underground, Thrinaxodon could have escaped the harsh Triassic sun, avoided the attention of larger predators, and perhaps found a stable microclimate to raise its young. Its teeth were differentiated, sharp canines for grasping prey, likely insects or very small vertebrates, and complex multi-cusped cheek teeth for shearing or grinding, hinting at a sophisticated diet. These small cynodonts were likely becoming increasingly active, perhaps developing higher metabolic rates, the beginnings of true warm-bloodedness. This would have allowed them to hunt for insects and other small prey during the cooler hours of the night or dawn and dusk, times when the cold-blooded archosaurs might have been less active. Think of them not as rulers, but as the small, adaptable mammals of their day, like the shrews, badgers, or foxes that coexist with larger predators in our modern world. They were specializing in the niches that the larger, perhaps less metabolically active archosaurs ignored, and within these small, perhaps nocturnal, perhaps burrowing cynodonts, the final crucial evolutionary steps towards true mammals were being taken. Their hearing was becoming more acute, with the bones of the lower jaw beginning the long, slow journey towards becoming the tiny, intricate bones of the mammalian middle ear. Their brains were likely becoming relatively larger, processing more sensory information. And perhaps, crucially, they were developing fur for insulation, and maybe even beginning to produce milk to nourish their young, though direct fossil evidence for these soft tissue features is incredibly rare. These cynodonts were playing the long game. They could not compete directly with the archosaurs in terms of size or brute strength. So they adapted, they specialized. They became masters of the small, the hidden, the nocturnal. They invested in energy efficiency, sensory acuity, and perhaps parental care. For the rest of the Triassic, and indeed for the entire 160 million year reign of the dinosaurs that followed, this would be the pattern. The Synapsid lineage, the lineage leading to us, would survive not as giants, but as small, adaptable creatures living in the shadows of the ruling reptiles. But they did survive. They carried the precious spark of mammalian potential through the entire Mesozoic era. They were the quiet, persistent counterpoint to the thunderous footsteps of the dinosaurs. Their story, beginning here in the recovering world of early Triassic Pangea, is one of resilience, of finding success not through dominance, but through adaptation, stealth, and the slow, patient refinement of the traits that would one day allow their descendants to inherit a world transformed once again. They were our distant, furry, perhaps night-active ancestors, holding the future within their small, determined forms. And the world around them, the great Pangea itself, was beginning to show the first signs of its own inevitable demise. Pangea, it seemed eternal. For nearly 150 million years, since its final assembly in the late Carboniferous, it had stood as the single defining feature of the planet's geography. A world united. The great mountain ranges formed during its violent birth had slowly eroded, their jagged peaks softening into rolling highlands. The extreme climates had perhaps mellowed slightly as global conditions fluctuated. Life, shattered by the Great Dying, had painstakingly recovered, diversified, and now the first true dinosaurs were taking their first steps across its vast plains, alongside our own small cynodont ancestors. It might have seemed to any hypothetical observer that this was the permanent state of the Earth. One land, one ocean. But the same forces that had driven the continents together were still at work, deep within the planet. The Earth's mantle, that vast, slow-churning ocean of hot rock beneath the crust, is never truly still. Heat, generated by radioactive decay in the core and mantle, constantly seeks to escape. This escaping heat drives convection currents, slow, colossal overturnings within the mantle that exert immense, relentless forces on the rigid tectonic plates floating above. For millions of years, these forces had conspired to push the continents together, closing oceans and building Pangea. But the configuration of a single supercontinent creates its own unique stresses. A supercontinent acts like an immense insulating blanket over the mantle below. Heat, unable to escape easily through the thick continental crust, begins to build up beneath it. The mantle under Pangea likely became hotter, more buoyant, perhaps even developing vast upwellings of superheated material. Mantle plumes. Imagine this immense, slow simmering heat building beneath the foundations of the landmass. The rock of the crust, under this intense thermal stress, began to stretch, to weaken, to dome upwards in places. And then, inevitably, it began to crack. This did not happen suddenly. It was not a single, catastrophic fracture. It was a slow, insidious process, unfolding over tens of millions of years, likely beginning in the late Triassic period, around 200 million years ago. Picture the first signs. Perhaps deep within the heart of the supercontinent, long linear valleys begin to form. These are rift valleys, places where the crust is being pulled apart, stretched thin like dough being kneaded. The land surface subsides along parallel fault lines, creating deep troughs. Volcanoes begin to erupt along these lines of weakness. Not the colossal flood basalts of the Siberian traps, perhaps, but persistent, localized eruptions pouring lava onto the floors of these growing rift valleys, a sign of the immense heat lurking just below. Earthquakes become frequent along these zones, the constant shuddering groan of a continent beginning to tear itself apart. These first cracks were likely not random. They often followed ancient lines of weakness, the very sutures where continents had collided hundreds of millions of years earlier to form Pangea. The old scars were beginning to reopen. One major zone of rifting began to develop right through the heart of the supercontinent, roughly along the line where Africa and South America had once joined North America and Europe. This was the nascent scar that would eventually tear Pangaea in two. Imagine the landscape transforming. Where once there was perhaps a dry inland plain, now a deep, steep-sided valley begins to form, kilometers wide, perhaps hundreds of kilometers long. Its floor is marked by fresh lava flows and steaming volcanic vents. Perhaps shallow, salty lakes begin to form within it, fed by intermittent rains or groundwater seeping in. This was not yet an ocean. It was just the beginning. It was the sound of the planet's crust groaning under immense tension. It was the first sign that the age of unity was ending. The great Pangea, which had seemed so permanent, so monolithic, was beginning to feel the irresistible pull of the mantle currents below. The slow, patient, and ultimately unstoppable process of fragmentation had begun. The supercontinent was dying, slowly, fissure by fissure, and from its death, a new world and a new ocean was about to be born. The cracks grew deeper. The rift valleys, born from the stretching heart of Pangaea, widened year by year, millennium by millennium. What began as shallow troughs cutting across the continental plains became immense, steep-sided canyons, their floors continuing to subside under the relentless pull from below. Imagine these valleys now, perhaps tens, even hundreds of kilometers wide, their walls towering cliffs of ancient rock, marking the raw, fractured edges of the separating lands. Volcanoes continued to erupt intermittently along their floors, pouring out basaltic lava, creating dark volcanic landscapes within the growing chasm. Lakes within these rifts grew larger, deeper, perhaps becoming vast inland seas, filled with water that was increasingly salty as evaporation concentrated the dissolved minerals under the Triassic and early Jurassic sun. For millions of years, this may have been the state of things, a continent deeply wounded, scarred by these immense, slowly growing terrestrial rifts, but not yet truly broken. A land divided by deep valleys, but not yet by a true ocean. But the stretching continued. The crust beneath these rift valleys became thinner, hotter, weaker, and eventually, inevitably, in certain places along this vast branching network of fissures, the continental crust stretched so thin that it finally tore completely. Molten rock from the mantle welled up directly into the gap. New, dense oceanic crust began to form at the bottom of the rift. And seawater began to find its way in. Perhaps initially it was just a trickle. A catastrophic flood event maybe, when a natural dam holding back the waters of the Tethys Ocean to the east, or the vast Panthalassa to the west, finally broke, sending a torrent of salt water cascading into the sunken rift valley. Or perhaps it was a slower, more gradual seepage, as the rift floor subsided below sea level, allowing marine waters to creep inland. However it happened, the moment seawater entered the rift, everything changed. The salty lakes transformed. They became narrow, elongated arms of the sea, reaching deep into the heart of what had once been a unified landmass. These were not yet the vast, deep oceans we know. They were likely shallow, perhaps restricted seaways, possibly prone to drying out periodically, leaving behind thick deposits of salt, evidence we find today buried deep beneath the Atlantic margins. But they were ocean. Marine life, perhaps initially hardy species adapted to fluctuating salinity, began to colonize these nascent seaways. The process of seafloor spreading had begun. Imagine standing on the cliffs overlooking one of these early proto-Atlantic rifts, perhaps somewhere in what is now the eastern coast of North America or the western coast of Africa. Below you stretches not a valley floor, but a narrow, perhaps intensely blue or turquoise strip of saltwater glittering under the Jurassic sun. On the far side, equally sheer cliffs mark the edge of the other continent, a continent that was, just a few million years before, part of your own land. Between you and that distant shore, new oceanic crust is being generated, slowly, relentlessly, year by year. The gap is widening, the continents are drifting apart. This was the birth of the Atlantic Ocean, not as a single grand opening, but as a slow, hesitant tearing. A series of narrow, interconnected seaways gradually widening, deepening, linking up over millions upon millions of years. The great sea shape of Pangaea was being broken. The northern half, Laurasia, North America and Eurasia, was beginning to separate from the southern half, Gondwana, South America, Africa, Antarctica, Australia, India. The sound of this event was not the violent crashing of the initial continental collision. It was perhaps a quieter, more insidious sound. The hiss of seawater hitting hot volcanic rock on the new seafloor, the constant low-level tremor of the crust pulling apart, the gentle lapping of waves on shores that were, millimeter by millimeter, moving further apart each year. Pangea was unraveling. The age of unity was ending, not in fire, but in water. A new ocean was being born between the fragments, an ocean that would grow, mature, and eventually define the shape of the world we know today. The Atlantic. Its conception was here, in the slow, patient tearing of the supercontinent. The birth of the Atlantic was not a singular event, but the beginning of the end for Pangea. The process of fragmentation, once started, continued relentlessly, driven by those same deep mantle forces that had first brought the lands together. The initial tear between Laurasia and Gondwana was just the first major split in the fabric of the supercontinent. As the young Atlantic Ocean slowly widened throughout the Jurassic and into the Cretaceous period, other rifts began to open, branching off, following old lines of weakness, gradually dissecting the remaining land masses. The great southern continent of Gondwana, which had remained largely intact through the initial breakup, began its own slow disintegration. Imagine new rift valleys forming, cutting across the land that held future South America and Africa together. These rifts deepened, flooded, and eventually gave birth to the South Atlantic Ocean, separating those two continents and creating the familiar coastlines we see today. Further south and east, other cracks appeared. Antarctica and Australia, still joined, began to pull away from Africa and South America. India, nestled between Africa, Antarctica, and Madagascar, started its long, slow, solitary journey northward, breaking free from the southern embrace, destined for a dramatic collision with Asia millions of years in the future. Even the northern landmass of Laurasia did not remain whole for long. A rift began to open between North America and Eurasia, a precursor to the North Atlantic, slowly separating Greenland from Norway, widening over tens of millions of years. The world map was being redrawn, piece by painful piece. Pangea, the monolithic giant, was returning to fragments. This process was not just about geography. It was about climate, and it was about life. As the continents broke apart, the harsh continentality that had defined the Pangea world began to lessen. New coastlines were created, bringing the moderating influence of the oceans deeper into the interiors of the separating landmasses. The immense central desert shrank, rainfall patterns shifted globally. The world, overall, likely became wetter, milder, perhaps more hospitable in many regions, and life responded. The dinosaurs, which had risen in the shadow of Pangea's recovery, now found themselves on separating landmasses. Their evolution began to diverge. The dinosaurs of South America followed a different path from those of North America or Africa, evolving into unique forms adapted to their newly isolated worlds. This fragmentation drove biodiversity, creating distinct evolutionary arenas where different creatures rose to prominence. The oceans, too, were changing. The opening of new seaways like the Atlantic created new pathways for ocean currents. The simple circulation of Panthalassa began to break down, replaced by more complex regional patterns. This altered the distribution of heat around the globe and changed the upwelling of nutrients, creating new opportunities for marine life. The Tethys Ocean, once a vast bay, began to transform, squeezed between the converging continents of Africa and Eurasia, eventually shrinking into the remnant we know today as the Mediterranean Sea. The great Panthalassa itself, though still immense, was slowly beginning its long transformation into the ocean basin we now call the Pacific. The legacy of Pangea is profound. It is written into the very shape of our modern world. The coastlines of South America and Africa still fit together like puzzle pieces, a silent testament to their ancient union. The Appalachian Mountains stand as the eroded roots of the colossal range forged during Pangea's birth. The vast salt deposits buried deep beneath the Atlantic margins mark the hesitant, evaporative beginnings of that ocean's opening. But Pangea's legacy is also written into the fabric of life itself. The distribution of fossils, like Glossopteris found across the southern continents, provided the first crucial evidence for continental drift. The Great Dying, triggered perhaps by Pangea's own internal stresses, completely reset the course of evolution, wiping out the dominant synapsids and paving the way for the rise of the dinosaurs. And the subsequent breakup of Pangea created the isolated stages upon which the unique faunas and floras of our modern continents evolved. Our world, the world of scattered continents and diverse oceans, the world of mammals and birds and flowering plants, was born from the death of that ancient supercontinent. We live today among the fragments of Pangea, drifting slowly on the same deep mantle currents that first brought it together and then tore it apart. The story of Pangea is not just a story of a lost world. It is the story of the birth of our own. It is the deep, slow prologue to the familiar chapters of Earth's history. And so, our long journey through the age of Pangea reaches its end. We have traveled across immense gulfs of time, hundreds of millions of years, back to a world fundamentally different from our own. We have stood on the shores of the single, globe-spanning ocean, Panthalassa, and felt the warmth of the sheltered Tethys Sea. We have ventured into the scorching, silent heart of the supercontinent's great desert, listened to the roar of its mega monsoons, and felt the chill breath of its southern ice cap. We have walked among giants long vanished from the earth. We met the strange, sail-backed Dimetrodon, the vast, tusked herds of Dicynodonts, the armored fortresses of the Parasaurs, and the terrifying saber-toothed Gorgonopsians, rulers of a lost world, echoes of our own distant ancestry. We witnessed the resilience of the early reptiles, biding their time in the shadows. We saw the rise of the hardy Glossopteris forests, a kingdom of green unlike any that exists today. And we stood as silent witnesses to the greatest catastrophe life has ever known, the Great Dying, a planetary firestorm born from Pangea's own geology, an event that nearly extinguished the flame of complex life entirely. We saw the strange, empty world that followed, dominated by the unlikely survivor, Lystrosaurus, and we glimpsed the dawn of a new era, the rise of the archosaurs, the first tentative steps of the dinosaurs, and the quiet persistence of our own synodont ancestors, hiding, enduring, holding the future within them. Finally, we watched as Pangea itself, that seemingly eternal monument to geological unity, began to crack, to stretch, to tear apart. We saw the birth of the Atlantic Ocean in those slow, widening rifts, the beginning of the fragmentation that would create the familiar map of our modern world. The story of Pangea is a story of deep time. It is a reminder that the world we inhabit is not static, not fixed. The ground beneath our feet is restless. The continents themselves are immense, slow-moving rafts, constantly rearranging themselves across the face of the planet, driven by the patient, irresistible heat of the Earth's core. Oceans are born, oceans mature, and oceans die. Mountains rise in fiery collisions, and mountains are slowly, inevitably worn down to their roots by the patient work of wind and water. To remember Pangea is to gain perspective. It is to understand that our fleeting human lives, even the entirety of human history, unfolds upon a stage that is itself in constant, slow transformation. The world was different before us. The world will be different after us. It is a humbling thought, perhaps, but it can also be a profoundly peaceful one. The dramas of our own lives, the worries and stresses of our day, seem smaller, less significant when viewed against the backdrop of these immense geological cycles, this slow, silent dance of continents across hundreds of millions of years. The world of Pangea may be gone, buried beneath kilometers of younger rock, its memory preserved only in the silent language of stone and fossil. But the forces that created it, the forces that destroyed it, are still at work today. The Atlantic Ocean continues to widen, inch by patient inch. The Pacific continues to shrink. The continents continue their slow, inexorable drift. The deep rhythm of the Earth endures. And perhaps, as you allow your mind to drift now, as you let go of the day, you can feel that rhythm. Feel the slow, patient movement of deep time. Feel the rise and fall of ancient mountains, the opening and closing of forgotten oceans. Feel the profound silence of the great dying and the quiet, persistent stirring of life returning in its wake. The story of Pangea is a story of unimaginable change, of catastrophe, but also, ultimately, of resilience. Life endures. The planet endures. Change is the only constant. And within that constant change, there is a rhythm, a slow, deep pulse, like the quiet beat of your own heart, slowing now, finding its own peaceful rhythm, like the gentle rise and fall of your own breath, carrying you now, softly, gently, towards the quiet shores of sleep. The ancient winds of Pangea have blown their course. The journey is complete. Rest now.